to you. He was the earlier director of Indira Gandhi Center of Atomic Research. He is a specialist in actinide chemistry and particularly the chemistry of nuclear fuel cycle. Dr. Rao graduated from the 16th batch of BARC Chemistry School and joined the radiochemistry division of BARC. He obtained his PhD degree in chemistry from University of Bombay in 1979 for his work on chemistry of actinide elements. He shifted to Indira Gandhi Center for Atomic Research at Kalpakkam in 1978 and rose to the position of director IGCAT and then superannuated in August 2015. He has over 300 publications in peer-reviewed international journals. Dr. Rao has guided 15 students for their PhD degree. Dr. Rao was selected for the Indian Nuclear Society Award in the year 2007 for his outstanding contribution to the nuclear fuel cycle. He was selected for the Material Research Society of India Medal in 1998 and the MRSI Senior Superconductivity and Materials Award in 2011. He was also selected for the Silver Medal of the Chemical Research Society in India in 2011. He was one of the vice president of MRSI during the tenure of 2015 to 2018. He is an elected fellow of Indian National Academy of Engineering and National Academy of Sciences, India. He was recently selected to deliver the prestigious H.L. Roy Memorial Lecture by the Indian Institute of Chemical Engineers. Dr. Rao founded the Southern Regional Chapter of Indian Association of Nuclear Chemists and Allied Scientists and has, through IEA and CAS, organized and taken part in a large number of programs in schools and colleges to educate the students regarding radioactivity and its applications. He also founded the Society for Advancement of Chemical Sciences and Education, SACSE, at Kalpakkam, and was the first president there. With this a brief intro, now may I ask Dr. Vasudev Rao to step over and share this. Thank you. Good morning to all, and thank you for the kind introduction. And it's a great pleasure for me to be here to meet you all on this very special occasion. I thank the organizers as well as the Central Office of HBNI with gratitude for inviting me to participate in this meeting and chair this session. We have 4 talks in this session, and as usual, these talks will be of total half an hour duration. And I request every speaker to restrict his presentation to 25 minutes at the most, so that we have enough time for discussion. We begin right away with the first lecture, which will be delivered by Dr. Arunasis Bhattacharya. You have the title of the lecture on the screen. Dr. Bhattacharya is presently an associate professor of HBNI and is working in the radiochemistry division of BARC. His research interest is the chemistry of the F block elements, especially to understand their separation and complexation behavior using both experimental and computational techniques. So he will be speaking on actinide chemistry, separation, speciation, and structural aspects. We keenly look forward to a lecture. Dr. Bhattacharya.
Thank you, Professor Rao, for this kind introduction. First, I would like to thank the organizer from BRC side and HBNI from neither side for giving me this opportunity to present our work on the actinide chemistry, which is being carried out in HBNI group. So, The actinide chemistry is carried out in HBNI group in three different divisions. I belong to this radiochemistry division, where we do the actinide separation using conventional solvent extraction, extraction chromatography, and membrane-based techniques, and recently we started selective dissolution of the actinides for their separation. Then actinide speciation, complexation in solution, as well as in solid liquid interface to understand the actinide sorption behavior using both experimental and computational approach. Then in fuel chemistry division also, the actinide separation and their determination is being carried out using electrochemical techniques. They mainly focus the electrochemical methods. Then actinide speciation in deep eutectic solvents and RTI media. Then actinide structural chemistry in the solid phase. In radioanalytical chemistry division also, the actinide sorption studies is being carried out, sorption and speciation and solid liquid interface. And they are also involved in the development of exam facility for carrying out experiments with actinides in IIT RRCAT Indore. This is the outline of my presentation. First, I will give a brief introduction about the coordination behavior of these actinides, some small introductions. Then I have divided this part in two different parts, early actinides and heavier actinides. Why I have divided this in two parts that we will discuss in the next slides. In the early actinides, we are carrying out this structural studies mainly in uranium, because we are not that fortunate that we can carry out that other actinides which are highly radioactive for the structural studies in the solid phase. Then solution phase speciation and complexation studies of this uranium. Then the next successive actinide is neptunium, that we can carry out the solution phase chemistry of this neptunium to understand its interesting complexation behavior. Then understanding the third phase formation behavior in actinide and extraction. Then electrochemical separation of early actinides, which is possible for early actinides. Then in heavier actinides, so in heavier actinides, that diglycolamide based supramolecular ligands is being used for the extraction of this heavier actinides. Then lanthanide actinide separation to understand their selectivity, and amnesium curium separation. This is a very difficult job actually. Then direct actinide lanthanide dissolution and estimation of these actinides and their separation. Then electrochemical and luminescence based detection and determination of actinides. Sorry for the interruption. Now, now you see, if we compare this coordination chemistry behavior with the transition metals, we are putting the two extreme. One is the transition metal and lanthanides. In case of the transition metals, we know if we know the metal ions, we know always the geometry. Suppose if we take a cobalt 3, so it shows that octahedral geometry if we change the even ligand also. But if we see in the lanthanides, suppose if we that europium complex of two complexes with the same ligand, whether with the same donor center, same density, but if we, even when we change that from nitrate to chloride, that coordination number changes from 10 to 7. So this kind of change in coordination behavior is observed in lanthanides because of their negligible orbital participations in bonding. So their bonding is mainly ionic bonding. So the direct, non-directional, and this that shows that different coordination behavior, coordination numbers and geometry based on the ligands. So, but actinides fall in between. So in case of early actinides, their covalence is observed, whereas in case of heavier actinides, they are mostly ionic bonding. The covalence is very small. So that's why we have segregated in two parts: the heavier, lighter actinides and heavier actinides. In case of now,
So if we see it's bonding uranium.
yeah. So if we see the bonding in uranyl, so which is a typical structure of, it's a linear structure. So this uranium oxygen bond is very inert. And if you see that oxygen isotope exchange, if you see that in acidic condition, this rate is very, very small. So, so to understand that, computational studies have been carried out to understand this bonding, and they have observed that the triple bond character in this bond. And these are the shapes of the angular distribution of this F orbitals, and this participates in the sigma bonding in this actinyl system, and these two orbital xz square and yz square, along with this dxz and dyz, they participate in the pi bonding, and that these two orbitals, they participate in this delta bonding, and these two orbitals participate in the pi bonding, resulting in the one dot overall bond order of 3. So that shows the very high covalency in this complexes. So this uranium complexation, that structural studies have been carried out in RC and IG, and they have observed that this bond they cannot play with, but this equatorial plane they can play with. And with this, some ligands they have synthesized, some that tetraalkyl urea-based ligands, and they observed that it is very highly selective for uranium. And that based on this, keeping this structure same, they have designed some other ligands where the pyrazine unit the two opposite side, this bifunctional, this ligand they have attached, and they could make the coordination polymers of the uranium for selective precipitation, which is required in some of the cases with very high kinetics, fast kinetics. Then uranium chemistry with some other ligands, NO and CO donor ligands also being carried out, where, and in this case, this similar donor center, but that in between they put some sulfur to quench this coordination polymer formation, where that don't require, so they can make the isolated molecules. Now, aqueous speciation of uranium in complexing medium is also being carried out in RCNDIG with some phosphonocarboxylate ligands using different spectroscopic, electrochemical, and XUPS-based and DFT-based calculations to understand their complexation, determine the complexation constants and their nature of the complexes. And that uranium complexation is also being carried out in deep eutectic solvents. So, using electrochemical and spectroscopic techniques. Now we are coming to the neptunium chemistry. In case, if we compare this neptunyl and uranium, the neptunium is a most stable oxidation state is +5, whereas uranium it is +6. So being the +5, this overall charge is, positive charge is less in this moiety as compared to this moiety. And that results in the more electron density on this oxygen compared to these oxygens. And so these oxygens can, it's known to interact with this other cation. So there is a interesting behavior of this cation-cation interactions, which also modulates its extraction behavior in the nuclear reprocessing stream. So there is a interaction between this oxygen with this cation. So there is two mode of interactions. One is that diamond type of shape. This oxygen interacts with this, and this with small interactions with this thing. And that is observed in the solid state, where that crystal packing also plays an important role. But in solution phase, we have observed that this is the main species observed in our case. So we have studied this, earlier we have studied this interaction in aqueous medium. Recently we have studied in room temperature ionic medium also, and we have observed, and this is the neptunium FF transition peak, which diminishes, and another peak observed in the complex, which is belongs to the complex of the uranium neptunium complex peak. And we have observed that interaction, that binding constant of this and this moiety, it increases significantly if we reduce the water content in the medium. It is the pure water medium, it is 1.76, the log beta value, but in dry RTIL it goes to 3.44. And we tried to model this thing using DFT calculations, and this bond if we observe this that oxygen, neptunium oxygen and uranium bond distance, which is 2.374 in water medium and reduces in the dry RTIL medium, and with enhancement in the bond order. So that shows that in strengthening of the interactions in the RTIL medium as compared to aqueous medium. So this is another example of a neptunium complexation with diglycolamide ligand. This will come about this ligand in the next after few slides, and we have observed that while titrating this ligand metal, that neptunium with this ligand, initially this peak of neptunium FF transition peak that reduces, and that after it completely vanishes actually. And if we see the complex structure, so this is the neptunium aqua complex. If we put that ligand 1:1 ligand, this is the complex, and if we see the 1:2 ligand, metal ligand stoichiometry, this is the complex where there is a presence of centrosymmetric. This is a centrosymmetric molecule, and that results in the reduction in the FF transition peak. So we can from the absorption spectra of the neptunium, that FF transition is followed to identify the nature of the complexes also. Another interesting thing is the third phase formation behavior in the actinide extraction. So third phase formation is nothing but, so the extractant we have dissolved in the organic phase for the extraction. Now, while it is being contacted with the aqueous phase, which contains the acid or metal ions, after picking up this acid and metal ions, that the solubility of this metal ligand complex or acid adduct of the ligand that reduces in the organic phase. That can be different, different reasons. Maybe one reason is the that aggregation of this ligand molecules in presence of acids or metal ions, or this the huge polarity increase in the complex, which reduces the solubility of this complex in the non-polar organic mediums, and that splits out from this organic solvents and make the third phase formation, which complicates the engineering processing of this metal ions for the separation. So here this is one ligand. This is a trinitriloamide ligand, which shows very high extraction for tetravalent actinides compared to other valence states. So we have studied, and this third phase formation behavior is more pronounced in case of tetravalent actinides. So we have studied to understand this third phase behavior of this ligand. So that small angle neutron scattering studies showed that this ligand itself present is a monomer, present is a dimer when it is in an endodecan medium. But when we put some decanol, which is a phase modifier, which is used to avoid the third phase, so that the polarity of the medium will increase. So that will result in the to avoid this third phase formation. And in this decanol medium, this is present as a monomer. Now, when this is contacted with the acid or this the metal ion in the aqueous phase, we have observed that in case of in absence of phase modifier, it is four these units are complexed. So it is a tetrameric micellar type of structure, reverse micellar structure is formed, and which results in the splitting of the organic phase and formation of the third phase. Whereas in this presence of phase modifier, this decanol, this is only dimeric complex is formed, which is soluble and remains in the organic phase, resulting in the we can avoid the third phase formation, which is also modeled using MD simulation. Then the electrochemical separation of early actinides. That electrochemical methods are well known for uranium separation in non-aqueous medium, but this cannot be used. This method cannot be used for in the aqueous medium because of this small electrochemical potential window. So and also metallic uranium reacts with the water. So they have modified that electrode with some other conducting polymers, and they could separate this thing. Suppose this is the typical waste which they encountered, which contains uranium, plutonium, thorium, zirconium, and other metal ions, along with these degradation products of TBP, which is well known for the extraction studies for actinides is being used. So and contains some carbonates also. So in that case, when they do that reduction processes, that plutonium 4 reduces to plutonium 6 reduces to plutonium 3, and which results in the formation of plutonium hydroxide, and that they could separate selectively. So they have used for the plutonium separation, and then another studies they have used from this uranium separation from in presence from the other lanthanide ions by the selective reduction of uranium to uranium oxide, not to uranium metal, which precipitates out, and they could separate it out successfully. Then we are going to heavier actinides, and where the F orbitals get localized, which is not available for bonding, and that results in the stabilization of low oxidation states. They are mostly trivalents, and their difficulty that results in their difficulty in their mutual separation because of their same valency states and very similar size, which is because already we have observed earlier that their interaction is mainly ionic interactions. So their interaction is governed by their ionic potential, but their size charge is similar. Their separation becomes more difficult. This is the ligand, which is till today this is the most promising for this separation extraction of these trivalent actinides or lanthanides both together. It extracts. But this is the most promising. If we see this the extraction profile along with the nitric acid concentration, which shows the highest extraction, this diglycolamine derivatives. But if we see their from the solvent extraction, we can calculate the metal ligand stoichiometry, which is responsible for their extraction. And if we see that this ligand concentration variation experiments, we have observed that 3 to 4 the DGA molecules are involved in bonding with this. We should not say bonding, we should the extraction of these molecules. So if we, it will be more interesting if we can. This is also people have studied that it is as a tetramer, it is extracting the metal ions, reforming the reverse metal. So if we can put this all 4 DJ units in same platform, then we can gain the entropy for the complexation, which where that metal extraction also can be expected. So keeping that in mind, the number of ligands has been designed and synthesized. So having 4, here 8, both sides, the calixanins and lower rim is derivatized, this is upper rim, and both the rims are derivatized. This is the tripodal benzene center tripodal ligand, so the 3 DGA moieties are attached. This is another kind of dendrimer types of things. Different generations, first generation, 0 generation, first generation, so the 3 and 6 DGA units and multiple DGA units are attached. And if we see this extraction values, this is the PO extraction with the TODGA, that's a single unit of this DGA moiety, and this is the extraction. And if we see this kind of ligand, so extraction significantly enhances. And in this case, even it's a very small concentration, we get very high extraction values. So that extraction, their extraction and complexation behavior is being studied by spectroscopic, then computational techniques, as well as that XUPS based techniques. So to understand their complexation behavior, and the theory also is used to explain their extraction and experimental behaviors. Then it's coming to lanthanide actinide separation. Because this ligand, whatever we have shown, the diglycolamide, it cannot differentiate between lanthanides and actinides. They show very similar behavior. So we have used some subdonor ligands which are known to be selective for actinides and lanthanides. So we have used this nitrogen donor heterocyclic ligands, which is an aqua-soluble ligands. If we put it in the aqua space, so whatever it will bind strongly with the fiber block elements, that americium it binds strongly. So that reduces ultimately the extraction of actinides, and lanthanide extraction is more. So that results in the selectivity between actinides and lanthanides. So to understand this complexation behavior, why this shows selectivity, we have done the spectroscopic studies using that. If we see that americium complexation, when that this is the FF transition peak for americium, which comes around 505 nanometer. If we put that ligand, the animation shows two different peaks. So that indicates that the 2 different damnation is present in 2 different environments. And if we do that, we have observed that species is M2L3 type of species we observed from the spectroscopy, that absorption spectroscopy titration. And then we have done that luminescence studies of europium complexes, europium complex, and we have observed the 2 lifetime values, indicating again that 2 metal ions in 2 different situations. Then we have crystallized this in neodymium complex. Here we are using this lanthanides as a surrogate for actinides because they are very similar chemical behavior. And we have observed this is the crystal structure of this neodymium complex of this ligand. And we have observed that in 1 unit, that 1 ligand is present, result is a cationic charge, because this is the 2- charge of this ligand. So that is a +1 charge overall, and this is -1 charge. So this is the ion pair type of form. And when we did the DFT calculations, we have observed that clearly higher covalent bonding in case of americium as compared to europium, and that results in selectivity of this ligand for actinides is explained the DFT calculations, and from other structural studies also it's supported. Then this separation, americium QM separation, is further difficult. Here, previous case, we have based on the 4f and 5f orbital differences, we could separate. But here, both are having 5f orbitals and very close ionic size, and they are successively they are placed in the periodic table. So their ionic size is very close. So their separation is further challenging. So we have used 3 ligands. This is aqua-soluble ligands. This where this is the tridentate, this is tetradentate, and this is also tetradentate, but with more rigidity. So now that if we see these are the aqua soluble, so they will hold an organic phase. We have used that diglycolamides, which is marginally selective for this curium compared to americium because of this slightly smaller size of this thing, and that results in the little higher extraction of curium if these ligands are not there. When we have put this ligand, that BTP based ligand, the tridentate ligand, it shows significantly high extraction of americium. So that means it holds the curium strongly. Whereas if we change this ligand to other ligands, we have observed that selectivity reduces, and in this case, it holds americium strongly compared to. So americium, it holds americium strongly, and this we could explain from the computational studies. If we take the competitive complexation of that diglycolamides and this ligand, we have observed that in case of BTP, it is this shows the negative complexation in overall energy. So that results in the favorable extraction of americium in case of BTP, and which switch over in other ligands. Then the direct dissolution and dissolution technique being carried out in a tail medium, where we have observed that in plutonium oxides is directly dissolved in this tail medium, and which is ultimately deposited on this planchet, and for the estimation, direct estimation of the plutonium from the oxides. Then we have also did the selective lanthanide dissolution in this for this lanthanide separation. We have earlier seen that americium europium separation is very difficult, but if we see the solid structure of this americium oxide and europium oxide is a fluoride structure which a very high lattice energy. The U by X is the energy required for the partial disruption of this lattice and formation of one free metal ion for MX OY type of this compound, and this value is for americium oxide. This is a 10,540 kilojoule per mole, whereas which comes another 6,000 kilojoule per moles in case of uranyl, which europium, which is cubic monoclinic structure. And based on this thing, we have done the separation studies on this europium and americium. And if we see this, at the time, the dissolution, that americium doesn't dissolve at all. It's a very small dissolution, whereas quantitatively europium is being dissolved. And this is the structure of the europium, dissolved europium complex. Yeah. So also we have done this electrochemical determination of actinides based on this cyclic voltammetric technique, which is a coupled reaction is responsible, and we could they could selectively estimate the uranium and plutonium in this analytical OS and these things, and which to overcome this redox spectrometry, which is commonly used, but they are complicated because of the presence of many metal ions. Also, that uranium sensitized to luminescence, europium luminescence is being used for the determination of europium, because you can see that in absence of europium, that it doesn't give any emission when it is excited with 320 nanometer, but in presence of uranium, because of close matching of the energy levels, it sensitizes the europium, and from there they could detect the uranyl in very small concentration in this process. So summary of conclusions of this thing, that as early actinides show variable oxidation states, redox chemistry and unusual interactions, very interesting, and in the influences their extraction separation behavior, improved electrochemical separation method developed. Several supramolecular DGA based ligands with superior extraction behavior developed for heavier actinides, lanthanides and complexation behavior using several spectroscopic and computational studies. Typical lanthanide and americium curium separations were studied by liquid-liquid extraction, direct dissolution, and electrochemical and luminescence techniques employed for the detection of determination of early actinides and lanthanides. And future outlook is the upcoming facilities is coming in exabytes for radioactive samples at Arakat Indore. The detailed understanding of the structure and bonding of actinide complexes will be possible. then playing in oxidation states, the stabilization of some unusual oxidation states of actinides will be very interesting to study and to understand the actinides with the bonding with these biomolecules. That is the upcoming phase. And this is the facility is being set up, and this is present hot commissioning is in progress in RFCAT for the studies of these radioactive actinide samples. That the contributors from radiochemistry, well chemistry, radioanalytical chemistry, and radiochemical isotope groups, and these are the collaborators for the synthesis and computational studies. And thank you all.
Thank you, Dr. Bhattacharya, for a very interesting presentation on a large number of studies related to actinides. I'm sure there'll be a few questions we can take up. Yes, please.
Okay, so nice talk, but I'm just curious about the handling of these actinides and also their cost, and can you please just give some kind of.
Cost means we cannot get from outside actually. Whatever we have to produce here using our nuclear reactors or this thing. So nobody will.
We cannot buy it from the market.
We tried once to buy ammunition 243. Even after coming that PO stage also it has stopped actually. We could not get because nobody is going to. Now the getting instrument is very difficult. So getting this
That's
kind of
what I'm curious
isotopes
about
is,
this.
whatever in-house we can prepare.
What about the handling of
those
actinides?
Yeah.
How do you handle the actinides? Is it precautions radioactive?
Yeah, radioactive, but if it is alpha active,
then it's
that
okay.
means we can just put some barrier, that's all, not much. But if it is a gamma active, then we have to put some shielding so that we can get exposure.
They can be very safely handled.
And, yeah.
Yes, yes.
It's a good talk. Just one doubt. In the case of NTA, you told it's very specific for +4 state. Correct? What is the reason for that? Is it because of steric issues? How do you design? Because normally you have +6 and +1 combination only is the one which is extracted.
Yeah, so because that NTA, if we see the structure, yeah, if you see the structure, I have shown is a linear, but it is a kind of tripodal structure. So this nitrogen in the top and this other the CO amide groups on the tripod actually. So it will not, that equatorial plane it cannot occupy. So if we take uranyl, that coordination will not be favorable. So that's why only.
Yes.
So you designed those dendrimers, no? So for the separation, right?
Extraction.
Yeah, for the extraction. So does those dendrimers have their own fluorescence or?
This one?
No, not that one.
No. They might have actually, but then you have to excite at very low wavelength actually.
Okay, but one.
That is metal fluorescence. Actually.
Yeah, but one, oh, that is metal fluorescence.
Metal fluorescence, European.
But did you check like after encapsulation of those metals? So whether this is single metal encapsulations or multiple metal encapsulations?
Yeah, that we do actually. Here we have observed. In other cases, we have seen a multiple metal encapsulation, not with dendrimers. In other ligands that.
Yeah, I'm talking about those.
Yeah, there we have not observed actually.
No, because they are nice because these are like polyamide amine type of ligands. So like they can actually capture more than one and make a clusters inside. And once they capture more than one, their fluorescence property changes completely.
Yeah.
Okay,
So fluorescence sensitization we have observed.
Okay.
Many cases we have observed very high sensitization.
Yeah, but I think actually you can study some fluorescence things, so that will give you a nice results also.
Okay.
Thank you.
One last question.
Very nice talk, Narcissus. Actually, was there any development on organic soluble BTPs where we can avoid this?
Yeah, people, because we have worked that aqua-soluble recently, maybe few years back. But in earlier we used to work in the organic solubles. So that has a solubility issues and all these things. So now people have.
They also have different types
of issues.
I was about to say that even this BTP, you have to change the aqueous phase to pH levels. Which,
this is not for actual process.
Yes.
That is
People may not like
yeah.
Anyway, I think we'll close the discussion at this point and thank Dr. Bhattacharya for a very interesting lecture. And on behalf of the organizers, I have great pleasure in presenting a small moment.
We now move on to the next talk by Dr. Madhava Malya, also from Pharmaceuticals Division of BARC. Dr. Malya completed his MSc in Applied Chemistry from Cochin University of Science and Technology, and he joined BRC Training School in 2001, and he got the gold medal for securing first rank in the BRC Training School. In 2002, after successful completion of training program, he joined Radiopharmaceuticals Division, BRC. His main area of research is the development of technetium radiopharmaceuticals, especially agents to detect tissue hypoxia. He is the recipient of several awards, including the DI Scientific and Technical Excellence Award, Dr. Tarun Datta Memorial Award, and DI Group Achievement Awards for his contributions. He has over 50 research articles in peer-reviewed journals and 3 book chapters. He is an associate professor at HBNI and regularly delivers lectures to the trainee scientific officers. He has also served as subject expert in overseas IAE regional training programs. It's my great pleasure to invite you to give the lecture. We are running short of time, but I'm not going to curtail your lecture, but please stick to your time and complete your lecture in 25 minutes. Thank you.
Thank you so much for nice introduction, sir, and very good morning. Thanks a lot for being able to participate in this interaction. So, as the title suggests, I'll give you an overview of radiopharmaceutical research in India. And unlike past 2 days, where we have seen exotic scientific discussion, you will not see anything like that for a change. I'll only show you very simple methods for the preparation of metal complexes, which have immense applications in human healthcare. So I belong to Radiopharmaceuticals Division of VRC. Primary mandate is production of radioisotope and cater to the radioisotope demand in our country. And we are also involved in research and development of and deployment of radiopharmaceuticals. So we have expertise in synthetic modification of potential molecules for radiopharmaceutical applications. We also optimize radio labeling procedures to make freeze-dried kits. We have also expertise in vitro and in vivo studies of these radiopharmaceuticals. So before proceeding further, I just make few assumptions. Since we are all from DAE family, I assume that all of you have basic idea about radioisotopes and also the radiations emitted by these radioisotopes and their application as radio tracers. So this presentation will almost exclusively depend on, I will be covering only the radioisotope applications in healthcare. So this cancer management is going to be a 21st century challenge because every day you hear the number of cancer cases in India is increasing day by day every year. So we require effective and affordable solution for diagnosis and therapy of cancer, and radiopharmaceuticals provide that effective solution. So what is a radiopharmaceutical? This is the schematic we generally see. You also must have seen it. Essentially, it has a targeting molecule and which is connected to a suitable radioisotope. And this also gives us the first opportunity to collaborate. If any one of you are doing your research to find that you have a molecule which has a potential anti-target property, you can collaborate with us. If you want to explore its use as a radiopharmaceutical, please talk to us. We can move together. So these are the 3 basic type of radiations, alpha, beta, and gamma, and these radiations can be used for diagnosis and therapy of cancer and also for organ function evaluation. I'll not be covering organ function evaluation in this presentation. I'll be mainly concentrating on diagnosis and therapy of cancer. So we'll just see how diagnosis procedure is done. So it all starts with the preparation of radiopharmaceutical, and then it is intravenously administered into a patient. The radiopharmaceutical is designed such that once administered into the body, it will localize in cancer lesion present which is present in the patient. And then with the help of a device called gamma camera, we scan the patient, which will determine the radioactivity distribution or radiopharmaceutical distribution in the patient's body. And a learned nuclear medicine physician can understand the spread of the disease. Also, you can take decisions on how to manage this patient further. So which radiation we will use for what purpose? This picture again you must have seen n number of times. Alpha, beta and gamma, their penetration. You know that alpha and beta doesn't penetrate at all, but gamma radiation shows very high penetrations. And for that reason, gamma radiations, because of their penetrating property, we use it for diagnostic purpose because ultimately we are interested to know what is happening inside the body. So if we want to know what is happening inside the body, we need some signal to come out of the body so that we can detect it and understand the process. So for that reason, we are using gamma radiation for diagnostic purposes. Now, what about beta and alpha emissions? Alpha and beta emissions have very high LET. LET stands for linear energy transfer. Linear energy transfer is nothing but the amount of energy deposited by the radiation for the unit distance it travels through any tissue. Now, human body is made up of cells, billions of cells, but every cell has many macromolecules in it, including DNA, RNA, etc. And these macromolecules are very essential for the cell to function and to survive. So now, these high LET radiations, if they can damage any of the macromolecules present in the cell, that can eventually lead to cell death. And that forms the philosophy of the radiation therapy. Now, this radiation can interact with cell in two ways, direct effect and indirect effect. Indirect effect, the radiation directly interacts with the macromolecules like DNA, which leads to single strand break and double strand break, and eventually it will lead to cell death. In indirect mode, the radiation interacts with the majority component in cell, that is water, 80% is water. So when radiation interacts with water, naturally it will undergo radiolysis. Radiolysis generates a lot of free radicals which are very reactive. These free radicals can also interact with the DNA and then take the DNA or make permanent damage to it, which will eventually lead to cell death. So far, so good. But how to send these radioisotopes to the target organ or tissue? Now, any local resident of Bhubaneswar, if I am asking them to go to Konark or something, they know the way. So they will know how to go, they will go on their own. But radioisotope doesn't behave like that. But I can show you one radioisotope which shows such property. Iodine-131. You know, all of us have got a thyroid gland. The job of thyroid is to make two vital hormones, T3 and T4. To prepare T3 and T4, it requires iodine. But our iodine cells, our thyroid cells, has got a special ability to absorb iodine from our diet. So suppose we want to analyze the thyroid of a patient, we can actually give him an oral administration of sodium iodide solution where this iodine, 131 iodine is radioactive. Now, if we scan the patient's thyroid, we will see that activity getting accumulated in thyroid because thyroid glands can absorb iodine from our body. So now, looking at these scans, a learned nuclear medicine physician can easily understand whether this patient is having a hypothyroidism, hyperthyroidism, or this patient is having a thyroid cancer. And accordingly, clinical management can be done. But apart from iodine, most of the radioisotopes, they do not know where to go or how to go to a particular target organ. So the situation is like somebody asking me whether I know how to go to Konark. I don't know because I am a resident of Mumbai. So in this case, what should I do if I want to go to Konark? What I can do is I can take some bus or I can take a taxi. So taxi is going or the vehicle is going to take me to Konark. We do something very similar in radiopharmaceuticals as well. The only difference is that in radiopharmaceuticals, we use molecules like peptides, hormones, antibodies, small molecules, or even many other enzymes So you can see, or you must have already seen the posters by Amit Kumar and Naveen, who have used these peptides and porphyrins. If you have not seen, you can see it today. They have done very interesting work in this. So now, how do these vehicles go to certain target? It is either by mimicking biologically active molecules or through interactions such as hormone receptor interaction, peptide receptor interaction, antigen antibody interaction, etc. Now I can give you one example, though we will not discuss it in detail. I can give you one example for mimicking biologically active molecules. Glucose, for example. Our cell requires glucose for its function. And now cancer cells, if there is a cancer, the cells grow very fast there, so they require more glucose. This has taken advantage of develop a molecule called FDG. Most of you must have heard about it, 18-fluorine FDG. FDG stands for fluorodeoxyglucose. The fluorodeoxyglucose behaves exactly like glucose, but that is radioactive. So once injected into the body, it preferentially go and localizes in cancer tissues. So that is how we are using it. Now, I will just explain targeting based on receptor interaction. First of all, let us see what is receptors. Receptors are nothing but proteins expressed on the surface of the cell. Now we can design peptides which can specifically go and bind to these receptors. And different type of cancers have got different type of this receptor proteins expressed on their surface. For example, for neuroendocrine cancer, we have somatostatin receptors. In breast cancer, we have estrogen receptors and herceptin receptors. Similarly, in case of prostate cancer, which is very prevalent in India, we have prostate-specific membrane antigen. So how do we find a ligand for targeting these receptors? Fortunately, we have some native ligands, that is ligands which are already present in the body, which gives us some clue what sort of ligand we have to look for to target these receptors. For example, as I already mentioned, somatostatin, a hormone produced in our body, it binds to somatostatin receptor. So that gives us a clue. So I can make molecules very similar to somatostatin, and they are highly likely that will go and bind to somatostatin receptor. So that can be my vehicle. In a similar way, folic acid binds to folate receptor, hyaluronic acid binds to CD4 receptor, so on and so forth. This is just 5 I mentioned here, but there are not many more. And suppose we don't know at all, or I want to develop a new ligand for a particular receptor application. What shall I do? In modern day chemistry, we have in silico methods to do that. I'm just briefly giving it here. The idea is that whatever receptor I am interested in, let us say somatostatin or folate or whatever, I can get the crystal structure of it from protein database. If I have this crystal structure of the receptor, I can just filter with take a library of molecules. Even library of molecules are nowadays available, like Sync database and all, which contain 20, 30 lakhs of molecules. So these molecules, I can apply some filters and check whether these molecules are likely to bind these receptors. So in my first pass, I applied different filters. What I mean by filters is that some certain structural features, electronegativity, etc., so on, lipophilicity, so on and so forth. So first I'll from 20, 30 lakhs molecules, I can narrow it down to few hundred lead molecules. And from that few hundred lead molecules, now I can do something called lead structure optimization. What I mean is that of that 100 molecules, now I will do something called docking studies. Docking studies is nothing but you are using these structures and trying to see whether they are fitting properly to the receptor proteins or not. Now, this docking studies is going to provide me information about the binding energy and the key interactions such as hydrogen bonding, pi-pi stacking, electrostatic interaction, etc. Now, if I understand the nature of key interaction between the lead molecule and the receptor, I can always tweak the design and make it much more, improve it further. Once I am satisfied with all these procedures, I can now embark into synthesizing these ligands and then test it in actual cancer cells. If they are really working on these cancer cells, then I can take it further for radiopharmaceutical development. And that is how things work nowadays. Now, does it really work? Yes, it does work. This is one work which we have carried out in our division. Yesterday you heard about PSMA 617. It's a ligand used for the preparation of lutetium PSMA. Now we want to develop a technetium analog of PSMA for diagnostic applications. Though we already have gallium labeled radiopharmaceuticals for prostate cancer imaging, they are very costly. In fact, radiopharmaceuticals are generally costly. Technetium is a very beautiful radioisotope for diagnostic purpose. So we wanted to develop a technetium-based radiopharmaceutical for diagnostic applications. So what we did was we kept the basic skeleton of the PSMA same and changed the ligand part. This chelator is called DOTA. This is modified with HYNIC, hydroxynicotinic acid. This is a small change, but that small change can actually result in non-binding of this receptor. So we want to test it even before we synthesize it. So what we did was, we did some talking study with the help of Somnath Kar. Some of you must be knowing him. You can interact with him to know further about this type of work. So this is the interaction, minus 9.4 kilocalorie per mole. It's the interaction energy of the original ligand PSMA 617 and the modified ligand, that is HYNIC PSMA. When we talked with this receptor, the same receptor, we found that almost similar or the same binding energy. So that gave us the confidence that it may work. Then we, with the help of bioorganic division of VRC, we synthesized this HYNIC PSMA ligand, and then we radiolabeled with the technetium, and we did the cell binding studies in prostate cancer cells, and indeed we found that they are binding very strongly with this cancer cells. Further studies are in progress, and we are very hopeful that this molecule will soon find it to the clinic in actual patients. Now, once we have the ligands, the next procedure is to bind a radioisotope to the ligand. Now, though it looks very simple, this process is called radiolabeling, and though it looks very simple, most of the time it doesn't work. Because most of these peptides, though they have large number of functional groups, if I want to put a radioisotope, simply mixing a radioisotope and then heating, it doesn't lead to radioisotope labeling. For that, we have to do some extra modifications. So we use something called bifunctional chelator approach. It is like, we have to put a chandelier on the ceiling. So what I do, I will first fix a hook, and to that hook, I will put the chandelier. Something similar we do here also. So the job of bifunctional chelator is like a hook. On one side, it will hold the biomolecule, and on the other side, it will hold a radioisotope. So this is another opportunity to collaborate. I know that there are many strong synthetic organic chemists sitting here. If you are interested, if your time permits, you can also look into developing new bifunctional chelating agents, which can be for chelators for lanthanides and technetium, that is in general transition metals. And if you can come up with very good bifunctional chelator, we'll be most happy to use them for radiopharmaceutical applications. Okay, here I am just running through some of the actual work that is being carried out. The TOC, tyrosine 3-nucleotide, it's an analog of somatostatin. So as I already mentioned, this cannot be directly radiolabeled, so I'll be modifying with a bifunctional chelator. In this case, it is DOTA chelator. So TOC, I conjugated to DOTA to get DOTA TOC. And this DOTA TOC can be radiolabeled with PET radioisotopes such as 68 gallium. Or later you will see it can even DOTA can be used even for radiolabeling with lutetium, yttrium, etc. And once we get this gallium DOTA TOC, this is the one which we use for diagnostic imaging for neuroendocrine tumors. Now suppose I want to label it with technetium, DOTA chelator will not work. So what I need to do is, my vehicle remains the same, that is tyrosine 3-nucleotide, but I will modify it with another bifunctional chelator which is called HYNIC, hydroxynicotinic acid. Then I will get HYNIC TOC, and this HYNIC TOC ligand and beautifully labeled with technetium in very high efficiency. And this HYNIC TOC can be used for diagnostic imaging of neuroendocrine tumor. So you can see that the same vehicle, but we keep changing the chelator. We can radiolabel it with different type of radioisotope as per our requirement. Now comes to technetium chemistry. Technetium is very, very important as far as nuclear medicine is concerned, because even now, even now, more than 80% of diagnostic nuclear medicine is carried out with this beautiful isotope 99 of technetium, which is obtained from 99 molecule. We can make chemistry because the chemistry was not very well known. So we take the ligand, we add technetium in the form of pertechnetate, add a reducing agent, and then either shake it or bake it, and then see whether any complex is formed or not. If a complex is formed, separate it and see whether it is having any biological activity or not. If there is biological activity, use it, otherwise throw it. And take another ligand and do the same thing. But now the chemistry has changed. Now there are well-formed, well-characterized, stable core of technetium that can be made. That is technetium nitrido, technetium ionic, technetium tricarbonyl, and technetium NS3. These cores can be made separately, whereas in this particular case, in the shake and bake chemistry, this technetium oxo cores are formed in situ, and we have absolutely no idea how it will form. We have to do it and then see it, what is forming. But here I can make all this cores of technetium, and after that, you can see some vacuum sites here. One site is occupied by technetium and nitrogen. The other 4 sites are vacant, and any of suitable ligands can be put here, and we can make it into a technetium complex. Yes, sir. Okay. So here there are just few examples where I've used technetium tricarbonyl core for radio labeling molecules with different type of molecules and small molecules and peptide with technetium tricarbonyl core. And this is the application of technetium nitrido core and NS3 core. And finally, I come to therapy. You understood how the diagnosis is being done. Therapy is not different. The only difference is that we change the radioisotope. For diagnosis, as I mentioned already, we use gamma emitting or positron emitting radioisotope. But when we use a radiopharmaceutical for therapy, our intention is to deliver therapeutic dose of radiation to the cancer site. So here you can see that the peptide remains the same, the chelator remains the same. We change the radioisotope from gallium to lutetium, and we are getting a lutetium of 98 labeled lutetium dotatate, which can be used for therapy of neuroendocrine cancers. This is, I'll just touch upon this antibody radio labeled with lutetium and 90 This is some of the work that's carried out in our division. Lutetium rituximab, 98 rituximab for non-Hodgkin's lymphoma. And recently we have also started work on BRCA antibodies because BRCA antibodies have some advantages over the old antibodies that we will discuss later also. Now, finally, the last slide. I have talked for the last 25 minutes. We are doing so many things. Did it really impact nuclear medicine in India? And out of so many different radiopharmaceuticals that we have indigenously produced, I have just took 4 out of them just to prove this point. See, technetium hynetone. 2008, there was no indigenous hynetone kit at all. Patients used to import it from Poland at a cost of nearly 30,000 to 40,000 rupees. But now the kit was available for 7,000 rupees at that point of time. Now it is after GST and all, it is 13,750. But still the imported price is 30,000. Nobody is importing nowadays. Has it made an impact? You can think about it. Lutetium dotatate injection for neuroendocrine cancer therapy. If a patient goes to a private hospital, will be charged at least 1.5 lakhs, whereas to BARC and BRIT, the same dose of radiopharmaceuticals can be obtained for 65,000. Same case with lutetium PSMA, which yesterday Diwakar Gopal mentioned. And recently, we have made 98 gem glass microsphere, which we nicknamed as Baba spheres. They are nothing but glass microspheres impregnated with 90 yttrium, which is used for treatment of liver cancer. Liver cancer is very prevalent in India, and so far, before the availability of Baba spheres, the patient has to import it from either Australia or UK for a prohibitively high cost of 7 to 8 lakh rupees per sitting. And the patient has to undergo nearly 1 or 2 such therapy sessions, which means that it is not for common man. But Baba spheres, which are made in ARC, will be available approximately at a cost of 3,000 only. So, and now think about it, whether it has made any significant impact on nuclear medicine in India. And you can be a part of it too. I mentioned already where all we can collaborate. So thank you so much. If you have any questions, I will be happy to answer them. And finally, let me also thank the work that I have mentioned here. It's not my work only. There are significant contributors, almost all the divisions contributing to our program. But I have mentioned only the seniors who are the leaders who generally carry this work forward. But my thanks to all my colleagues in Radio Pharmaceutical Commission here. Thank you so much.
Thank you, Dr. Malaya, for a very fascinating and very lucid presentation with very important results for the scientific community as well as the country. Are there any questions? Yes, please.
Dr. Madhav, myself, Malo, excellent talk and several things I have learned. I have in general question. So you see, we read that, at stage 3, stage 4 cancer, a lot of celebrities go outside. And I don't know much, but we feel that probably they are going outside and survival rate or curing rate, whatever you say, is better. So what is the reason that, when they are going there, which we cannot, possibly we cannot do it here in India? If you can comment.
Okay, yeah, sure. So I can. There is nothing like which we cannot do here and which is available outside. Probably one problem that I can tell you is that so far, though I am telling that we cater to the demands of our country, because of so many reasons, we are surviving with only one reactor. So one reactor cannot sometimes cater to the needs of the entire nation. So for celebrities, they cannot wait. Common man can wait. So what they are looking for is the facilities and the ease. They should get the medicine very easy. For that reason only, they are doing it probably. Otherwise, I don't know any statistics where somebody has survived because they have gone outside and not because of it. And in fact, I can tell you, there is something called medical tourism nowadays. Medical tourism means many from the Gulf countries and even from abroad, not even from they are coming to India for therapy because therapy cost is less here. So it is not completely true that, okay, celebrities may be going because they have a lot of money, they can afford to do that. They are doing medical tourism there, but there are many people who do medical tourism here in India. But there is a lot of scope for improvement. We have to make things available. We are trying our best to do that, but still there is some way to go. Yeah.
Any other questions? Yes.
Hello, I'm Peru. Nice talk. Just I want to curious to know about it. So we have the molecule which has shows the anti-cancer property. Can you label that molecule? Can you test it? Is it possible?
Yes, that answer is not so straightforward. Unless we look at the structure, we cannot determine how exactly to label it. Now, any molecule you take, the anti-cancer activity is because of certain groups in that molecule, correct?
Yes.
So first of all, we should have an idea about them. For example, I have shown you some peptides here, but we are modifying that peptide at a particular location only.
Yes, yes.
Know that certain part of the peptide is very important for showing that binding with the receptor. In a similar way, you may be having a molecule. First of all, you should have an idea what part of that molecule is actually interacting with the receptor.
What is we know that one where it is interacting.
Fine.
The other side, can you label it? We can see
Of
the
course,
best.
it can be explored. I will not tell you that immediately the molecule, like I showed the shake and bake chemistry, that you cannot do. I mean, you cannot just mix the radioisotope and radiolabel it. That's not possible. Okay. Looking at the molecule, it may be possible that we have to modify the molecule on that part which is not involved in binding or the anti-cancer activity, and then radiolabel it. But certainly it is possible.
Thank you. Yeah, we will talk to him later.
I think we'll take other questions during the break. Even though your presentation is very, very important, I'm sure a lot of people would like to know more about it. Thank you very much for a nice talk. On behalf of the organizers, I would like to make a small presentation.
Thank you so much.
We now come to the third talk of the session to be delivered by Professor B.L. Bhargava from the School of Chemical Sciences at NICE at Bhubaneswar. He obtained the MSc degree from the University of Mysore in 2003 and PhD degree from Jawaharlal Nehru Center for Advanced Scientific Research at Bengaluru in 2008. He carried out postdoctoral research in the University of Pennsylvania during 2008 to 2011. And his main research interest is in computational studies of soft condensed matter and biophysical systems. Dr. Bhargava, please.
Thank you, Professor Rao, for the nice introduction. So, first, I would like to thank HBNI for organizing this meeting, to come up with the idea of organizing this meeting. I would also like to thank the convener, Professor Sharanappa. So, he has worked tirelessly to make sure that the event goes without any hitches. So, in the next 20 minutes or so, I will be talking about some of the work that is done in our lab very recently in the past 2 years. So, yeah. So in chemistry usually, so the first thing we come across is that you do experiments. So you can also study the properties of the systems using another method, which is computation. So we model the system, so and look at the properties of the system from the molecular point of view. So depending on what we are interested in, so some of the phenomena may happen over long time scales and some may happen over short time scales, and the size of the system may also be different. Depending on the system, so there are different methods which can be chosen for this. So I will be so depending on the process that we have to study, so we can choose any of these. So as we go to quantum mechanics, so we can get more details, so electronic structure and all. If you have bigger system, you can use atomistic simulations, and if you have still bigger system in the micrometer range, so we can use post-graining, and beyond that we have to use the continuum model. So what in our lab we deal with atomistic simulation, and we also do some quantum mechanical calculation as well as post-graining. But in this particular talk, I will be focusing on the results obtained from the molecular dynamics simulation. So in our lab we work in several condensed phase systems. So you can term it as condensed phase computation, and some of the systems we are interested in are deep eutectic solvents and surfactants and so on. So we study the structure and dynamics in the condensed phase of this complex system. But what I will be talking today is not about this, but some biophysical systems. So these are some of the polypeptides which are involved in the neurodegenerative diseases. So one of them is the amyloid beta peptide, so which was known from the beginning to be responsible for the Alzheimer's disease. And the another peptide I would like to present the results on are the tau fibers. So what do we do here? So we have a system and we want to model it from the molecular point of view. So if you have a system, so it will have some molecules, and each molecule will have atoms. And if we know the interaction between these atoms, so then we can compute the force acting on a molecule, and then all you have to do is to integrate Newton's equations of motion to get the position and momenta at a future point in time. So this is a deterministic approach. That means once you know your initial configuration and the forces acting on the particles, then you can determine the entire future trajectory of the system. So for that, the problem is you will have to know the potential of interaction. So how different atoms in your system will be interacting with other atoms. We have bonded interactions, which are due to covalent bonds, and non-bonded interactions. So these are due to the Coulomb interactions, and then we have dispersion interaction. If you have any two atoms, so there will be interaction between these two atoms, so which we generalize using some analytical form, which is known as this is the Lennard-Jones-Felsick form. So what we need is that we need initial state of the system. That is, you have to provide the initial position and velocity, and you can determine the time evolution of the system. So the advantage of this is you can also couple this with thermostat and barostat, which will mimic the constant temperature or constant pressure, that is experimental conditions. And if you have the trajectory, so you can get all the required properties from this trajectory. All the macroscopic properties can be obtained from the trajectory. So this is one of the system of interest. What are these amyloid beta peptides and why should we study them? So these are known to be responsible for Alzheimer's disease, and these are formed from the proteolytic cleavage of amyloid precursor protein from beta and gamma secretases. And there are few varieties of these products. They vary from 39 residue to 43 residue, but the 40 and 42 residue peptides are dominant. These are also intrinsically disordered proteins. So this is the term I will be using. So what it means is that they do not have a fixed three-dimensional structure. So whatever I have shown here is the crystal structure. However, if you put it in water, it will not retain the structure. So it is very flexible. So since it is very flexible, the conformational sampling of these will be difficult. We will have to sample a lot of phase space to get the proper average for the system. So they are major component of extracellular neuritic plaques in Alzheimer's disease, and the A beta 1 to 42. So this forms oligomers, and they say that this is the more dominant species in the protofibrils. So there is also high prevalence of metals in the fibrils that are found in the brain, these dementia affected parts of the brain. So this is again the crystal structure of the fibril, and what we do here is to study the effect of Zn2 plus ion on the structure of this amyloid beta protein. So since these are intrinsically disordered proteins, so we will have to sample a lot of phase space. So for that, what we have done is we have done 4 independent simulations, each of 1 microsecond, and with and without the presence of zinc ion. So these are the computational details. We have used GROMAX software. We will not go into the details, but we have simulated about 9 microsecond, which is a large time for atomistic simulations. And the systems are also not small, so these have around 200,000 atoms in each of these systems. So here, these are the structures of the peptide, polypeptide after 500 nanosecond and 1 microsecond. You could see the crystal structure. We started from this, and during the simulation, so this is without zinc and this is with zinc. So what we see after 1 microsecond is that so the secondary structure is entirely vanished after 1 microsecond in the absence of zinc, whereas we still find some secondary structure in the presence of zinc. So this is the same thing shown as a function of time. So this blue color is the alpha helix. You can see that it is retained until the end of the simulation. So we can say that the zinc conserves the Zn2 plus conserves the secondary structure. So we can also do other things, that is to what I have shown earlier is from the equilibrium simulation. So you can also get the free energy from this. So we can do non-equilibrium simulation. So for that we calculate the potential of mean force. So if we have something in a solution, so the surrounding in the, let's say we have a molecule, this is oil water interface, and we have a molecule here. So the surrounding will be changing. At every instant you will have different surrounding, and therefore the force acting on this molecule will also be continuously changing. So potential of mean force will actually get you the potential which is the average over all these configurations. You average the force on the molecule. So due to different surroundings, and then the potential corresponding to that force will give the potential of mean force. You hold some degrees constant and average over all other degrees of freedom. So in this case, let's say we have oil water interface. I can move this molecule from oil to water, and at any given point, so I can compute what is the free energy. So the Jarginski's equality will actually relate the work done to the free energy of the system. So by calculating the potential of mean force, we can actually get the free energy preferences in many biologically relevant processes like stretching of proteins, pulling small molecules or ions through the ion channel, and so on. So we have done one such thing. So what we have done is we took the crystal structure of A beta 1242 in the solution, and it has two alpha helix connected by a turn, and then we pulled it with some force. We pulled both the ends to unwind this peptide. So this is done at 0.2 nanosecond, 0.2 nanometer per nanosecond. So it's actually a fast pulling only in the microscopic scale. And in pulling this, so we took 100 different points in this, and then again we equilibrated for 10 nanosecond at each point to get the free energy of this. So as you can see, so as we pull, how the secondary structure is changing. So this is without zinc and this is with zinc. What we see is that the C terminal undergoes unwinding readily. So initially C terminal unwinds and then the N terminal. So here I have shown the free energy profile as function of end-to-end distance. As we pull, how the free energy of the system changes. So as you can see, so the free energy for the monomer without zinc is around 46 kcal per mole, and with monomer and zinc, it is 37.09 kcal. So we also did the steered MD calculations for pulling the Zn2 plus away from the peptide. So for that, we can find the binding free energy in the solution. So if you do gas phase calculation, it will be different. In this case, we have the solution which will be interacting with the molecules. So in presence of solution, what will be the binding energy? So the binding free energy was found to be around 9 kcal per mole. So there is significant binding of Zn2 plus ion to the amyloid beta protein. So next I will talk about another polypeptide which is responsible for many neurodegenerative diseases. So these are tau fibrils. So tau is tubulin associated unit, and it is present in the axons of the neurons. So healthy neuron will look like this, and you have the tau proteins bound like this. So if they aggregate and form neurofibrillary tangles, so then the axon will not be, these microtubules will not be stable. These are also intrinsically disordered protein, and usually the hyperphosphorylation leads to the aggregation of these and forming the tangles. So these are the degenerative diseases which shows abundant filamentous tau inclusion. These are known as tauopathies, and there are many examples of these: Alzheimer's and progressive supranuclear palsy, fixed disease, and many more. So these are now attracting the attention of researchers because these are associated with many neurodegenerative diseases. So this tau fibril, so they can actually exist in two alloforms, so two polyforms. So one is the straight filament and another is the paired helical filament. So both of these contain exact same residues, that is 306 to 378 from the tau protein. So only difference between these two polymorphs is the way the dimers are binding to each other. So these are called paired helical filament because in the fibril, so two of these units will form a helical pair, whereas in this case they just form a straight pair. So this is the initial configuration. So we took the fibril. So this is also crystal structure which has 10 units in the fibril. So 5 on each side. So we took this in a membrane. So which is the model for lipid bilayer. So we put it over the top of the membrane, and we wanted to look at how the membrane composition affects the structure of the tau fibril. So these are the details of the system. We studied in 7 different bilayers, and as you can see, so the number of atoms is very large. So with this, and we have also done control simulations without this. So shown here is the bilayer thickness. So it is like looking from the top of the bilayer, and we have shown the profile. So at each point, what is the bilayer? You can see the scale here. So this is POPG and this is POPG plus cholesterol. So the tau fibril, this is the straight filament fibril on top of. So what is observed is that the type of tau fibril deforms the bilayer which is surrounding it, and the presence of cholesterol actually increases the bilayer thickness in the surrounding of the fibril. The protein is also seen to perforate the bilayer in the internal surface. So we looked at the stability of the fibril. So this is the root mean square deviation, and it was found that the simulations are converged after 30 nanoseconds, and these two are the most stable ones, POP plus cholesterol and POPG plus cholesterol. And the angle of coverage, which they have defined the angle of coverage by 3 residues. So this will determine whether it is flexible or not, and it was found that this depends on the lipid composition, and the inclusion of cholesterol actually increases the angle of coverage. So we looked at the secondary structure. So these are the number of beta sheet residues present in different lipid bilayers, and it was found that the negatively charged lipids have more beta sheets, and it is highest in POPG plus cholesterol. And you have 10 fibrils, but the number of beta sheets changes in the lowermost peptides, which are bound to the bilayer. So the local changes are actually more important compared to the overall structural changes. So then what we did was to look at these tau fibril in the model neuronal membrane. So model neuronal membranes will have, it will not be a, it will have different lipids in the bilayer. So this is the composition. We have POPC, PSM, POP, POPS, GM1 and cholesterol in certain ratio. So we looked at both PHF and SF in presence of the neuronal membrane. So what we found was that the PHF is more stable than SF, and actually neuronal membrane stabilizes the fibril more than the water membrane. And we looked at the fibril in membrane interactions, and the positively charged residues are closer to membrane in the PHF, and PHF also approaches closer to the membrane. So that is what is shown here. We have plotted the distance between the fibril and the membrane as function of the contacts, and we see that the number of fibril lipid contacts actually increases with closer approach, and the intrafibril contacts is greater than the PHF membrane. So again, other structural quantities, that is radius of gyration and solvent accessible surface area. So yes, straight fibril is more compact in water, and straight fibril is also more soluble than PHF in the neuronal membrane. The binding of the tau protein to the membrane makes it more compact. We also looked at the intrafibril interactions, and there are some specific interactions which are responsible for the stability of the dimer. So what we saw was that this particular interaction L315K31 decreases, whereas K317, K321 increases from the cryo-EM structure for the SF structure. Again, we looked at the secondary structure of the both straight fibril and the paired helical filament, and what we found was that they show the contrasting behavior, and C-terminal region show maximum change from the cryo-EM structure. So we looked at the interaction of the tau protein with different lipids of the membrane, and what we found was GM1 is the has most contact, followed by POPC, and the trend is similar for both the polymer, and they interact with the area per enhancement basically in luminescence contains in heavy water basically. So what I mean to tell basically here, so there are two problems now. First one was epsilon value was poor in case of lanthanoid, and second one is that even some epsilon is there, this emission is going to become non-radiative because of this quenching process. So now question is that how to enhance the luminescence of lanthanoid ions. So problems are there. So one problem is that the absorption coefficient of lanthanoid is very, very low. And then second one is non-radiative deactivation. So this lanthanoid luminescence can be enhanced by using, first problem can be solved by using ligands. So you bind ligands to the metal ions. And if somehow ligands absorb light and if they transfer light energy to the ligands to the metal ions, you can enhance the luminescence. And this phenomena basically we call ligand sensitized luminescence. And second thing is that you can decrease the non-radiative process where you can replace water molecules by using synergistic agents, where you can have low energy oscillators, not unlikely OH oscillators. So this is the ligand sensitized diagram I have shown. So in order to choose ligand basically, so there are some criteria how to choose ligands for efficient ligand sensitized luminescence. So there are 4 criteria. One is intersystem yield of ligand from 4 should be high. It means similar to triplet. This efficiency should be high because energy transfer occurs from the triplet level to the emitting level. So if this is not high, your ligand itself is going to show fluorescence. We don't want this thing. And then ligand should have matching triplet state levels. So it means the energy levels should lie above the emitting level of your metal ion. If it is below, it cannot transfer the energy to metal ion. And third one is that ligand should have a high absorption coefficient. So you should have a quite good amount of epsilon value. Otherwise, it will not absorb much light. And fourth one is ligand chromophore should be in close proximity because energy transfer is a function of distance between donor and acceptor. Now coming to the particular in the case of europium, which I am going to deal with, europium luminescence in aqueous medium. So these are the energy levels which involve in the luminescence. So you get basically different emission peaks from 5 to 0 to different levels of 7F, and these are typically spectra I have shown of europium in aqueous medium. So you get different peaks 5 to 0 to 7, F0, F1, F2, F3, F4. Out of these basically this transition 5 to 0 to 7, F2 is very important to probe the coordination environment because it's the electric dipole transition which is hypersensitive in nature. So what does it mean? It is very environmental sensitive. So this is in water. So for example, if I change the environment, this intensity is going to change. And in luminescence spectroscopy, we take the ratio of 5 to 0 to 7F2 to this transition, which is magnetic dipole in nature. It doesn't change with the ligand. So we take this ratio, which is called as asymmetric ratio, to probe the environment. Moreover, luminescence lifetime also can be used to probe the coordination chemistry of your lanthanoid because lifetime is also well sensitive because lifetime is number of how many water molecules are coordinated to your europium. And even people have proposed some equations, some empirical equations. Once they know the lifetime of europium, they can tell how many water molecules are getting bound or how many water molecules are coordinated at inner sphere by using this equation. This equation is a Chopin equation basically. They have modified the original Horowitz formula. So it means this luminescence spectroscopy is excellent tool to study the to study the coordination chemistry of lanthanoids. And here I have shown how ligand sensitized fluorescence works too. You see the europium in water medium. So generally these are the 9 water molecules are bound with europium, and this is the fluorescence luminescence spectra of europium. Lifetime is around 110 microseconds. Asymmetric ratio this peak to this peak around 6. Number of water molecules. Again, you can calculate by using previous equation, whatever I have shown you, Chopin equation, the number of water molecules 9. The moment you add ligand, some of the water molecules are getting replaced by ligand, and now you see this peak 5 to 0 to 7F2 transition. Its intensity goes up because the environment is entirely changing, and lifetime has become now 350 microsecond. And again, you apply same equation, you can get the number of water molecules. And if you replace again by the water molecules by some synergistic agents. For example, here I have used topo, thioctyl phosphinoxide, and you can see the lifetime 1110 microsecond. It means if you calculate number of water molecules, there are 0 water molecules. So it means basically you are probing the coordination chemistry. At the same time, you see the enhancement. So here typically counts, and I believe here europium concentration is same. So intensity is around 100, and you see around intensity 25,000. So around 50 times enhancement is there because of the ligand sensitized fluorescence. And again, this enhancement 25,000 to around 250,000 enhancement is due to the use of synergistic agents. And in our laboratory, basically, we have used different ligands like benzoic acid, substituted benzoic acids, beta diketone based ligands to enhance the luminescence of lanthanoids because these find analytical application in various fields. And here some of our publications in last 6 to 7 years where we have applied this ligand sensitized fluorescence to detect europium at trace level. And in our laboratory by using efficient ligands, sometimes we change solvent, sometimes we change synergistic agents also. So we have detected europium even at the level of parts per trillion. Now coming to the main topic, that is coordination chemistry of lanthanoid complexes, because this is very important in various fields such as separation chemistry, biology, and because such kind of interactions are very important. Interaction between metal ion and ligand is very important with respect to extraction and separation of lanthanoids. Also, this interaction between lanthanoid and ligands are very important for the to study the migration behavior of lanthanoids in soil. Suppose you have some geological deposits of lanthanoids and actinoids, and suppose it floods. So how basically these lanthanoid actinoid goes in the environment? Again, such kind of interactions are very important because in aquatic environment we have humic acids. So how these acids bind with your europium or ligands, such kind of interactions are very important. And if you see the literature, so in literature basically oxygen, sulfur, and nitrogen based ligands are particularly studied because these atoms based ligands are the model compounds for humic acid which are found in aquatic environment. So in my talk, basically, I am going to deal with first kind of ligands, which is basically furon carboxylic acid. So here I will be talking about two ligands, two furon carboxylic acid and three furon, and same results we have obtained for hyophene based carboxylic acid. So I will not talk about these ligands. I will be talking about only 2-FCA and 3-FCA. So here I have shown the luminescence spectroscopy data of europium bound with 2-FCA and 3-FCA. So this is the excitation spectra of europium of the concentration of 5 to 10 to the power minus 3 molar. And here you can see the different bands due to the 4F transitions. And now this excitation spectra is corresponding to the europium complexes of with the 2-FCA, green in color and red in color in 3-FCA. So what basically you are seeing that in excitation spectra of the complexes, you are getting the band, and this band is due to pi-star transition of your ligand ions, and these bands are no longer seen because the concentration is very, very less. And if you see the enhancement factor, again, there is a huge enhancement. If you see intensity here 4,000, here intensity 12,000. And also if you see the concentration, here concentration is around 250 times less, still enhancement is more. It means there is around 2 to 3 orders of enhancement. And this enhancement is due to the antenna effect. Ligand is absorbing and transferring the energy to europium. Same thing is followed in emission spectra also. And but quite interesting thing is that in case of 2-FCA, the intensity is around 6 times more compared to 3-FCA. So why it is so? For that purpose, we have used absorption spectroscopy and we have measured absorption spectra of both the ligands, and we found that 2-FCA has more epsilon compared to 3-FCA. So it means this ligand 2-FCA absorbs more, and that's why we are getting more luminescence. Now coming to the complexation studies. So we have carried out complexation studies europium by using these ligands. So what we have done, we have recorded different emission spectra, different ligand to metal ratio. And here I have plotted the asymmetric ratio versus ligand concentration. And you can see that this ratio is keep on increasing. It means environment is changing. And then such kind of inputs we have paid in the software, hyper-quad software basically, to indicate the formation of which kind of complex is formed. So we have that software indicated that it's forming ML complex, and also it gave the stability constant. So in case of europium 2-FCA, 1.24. In case of europium 3-FCA, we got the stability constant 5.4. Now, what is the coordination modes basically? So in case of 2-FCA, one can expect these three modes. So bidentate this ligand through 2 oxygen atoms of the carboxylate, or bidentate 1 oxygen of carboxylate and 1 this ether oxygen, and one more possibility is there, monodentate. And in case of 3-FCA, basically this possibility is not there because this ether oxygen is wiped away. Only two possibilities are there. Then we have probed which coordination modes is exactly forming here, and for that purpose we have done lifetime measurement. So lifetime we got around 120 microseconds. Again, you calculate number of partner molecules, so number of partner molecules are coming around 8. So it means only one water is getting replaced by ligand. So it means if ligand is bonded to europium in a monodentate fashion, it has to be like this only. In both cases, we got around 120 microseconds. Further, in order to prove, we have plotted basically LEFR plots. So this is nothing but linear energy relationship plots. And according to LEFR, the interaction between europium and ligand is electrostatic in nature. So europium 3 plus is like your Lewis acid, and then ligand is like Lewis base. So more the value of pK, more should be the stability constant. So here I have collected data from the literature. I have chosen the ligands which show the monodentate binding, which bind basically with europium in a monodentate fashion. And these data of europium 2-fluoride and 3-fluoride fits in linear, and we can say that it is also binding in a monodentate fashion. Then I have done some theoretical calculations. Again, we have geometry, we have optimized geometry, and from theoretical calculations also I found that this is only, the binding is through only one oxygen of carboxylate. And we have proved that ethyl oxygen does not participate in bonding even in case of 2FCA. Then complexation energy we have calculated, and we found the complexation energy in case of 2FCA is around 1 minus 1.5, 3FCA is 119. So this is in highly agreement with the experimental or log beta values obtained through experiments. Now coming to the second part, second kind of ligands, where we have used pyridine-based dicarboxylates. So again, we have used two kind of ligands. One is pyridine 2,3 dicarboxylate, pyridine 2 and 3 dicarboxylates, and pyridine 3,4 dicarboxylates probe the coordination environment of europium. So this is the luminescence data. So this is the excitation spectra. So this red color shows, this black color shows the excitation spectra of bare europium. So you have only 4F bands. And this red color shows the excitation spectra of 2,3 PDCA. Blue color shows the excitation spectra of 3,4 PDCA. And again, you can see there is a huge enhancement in the intensity basically, and it is reflecting emission spectra. So if you see the luminescence intensity of 2,3 PDCA is almost double of that of 3,4 PDCA. Then we have recorded absorption spectra. So absorbance is almost same. So it means there is some other reason why you are getting almost double intensity. So we have done some complexation again study on that. So in order to perform complexation studies, again we have carried out luminescence titration, where we have varied different ligand to metal ratio, and we have plotted basically asymmetric ratio versus ligand to metal ratio. So this plot shows in case of 2,3 PDCA. So basically, if you see the asymmetric ratio, so it reaches, like it starts from 0.5, it reaches up to 6.5 in case of europium 2,3 PDCA, and it reaches around up to 2.5 in case of 3,4 PDCA. Then these data, so this data basically we have feed in the software again to find out the stoichiometry as well as stability constant of the formed complexes. And we found that in case of europium 3, europium 2,3 PDCA, there are three kind of complex ML, ML2, ML3, and these are the corresponding low K value. While in case of europium 3,4 PDCA, we have only ML and ML2. And here I have shown the speciation diagram, how these ML, ML2, ML3 are evolving with respect to the ligand concentration, and you can see at the higher concentration, highest stoichiometry complex is dominating. Then we have carried out lifetime measurement studies to some shine light on again some kind of bonding, how it is getting bound with europium ligands, and we found that the lifetime of europium basically reaches around 450 to 500 in case of europium 2,3 PDCA, and in case of europium 3,4 PDCA, lifetime reaches from 110 water medium to around 170 3,4 PDCA. Again, we have applied this equation, Chopin equation. So in case of europium 2,3 PDCA, number of water molecules are 2. So assuming what is the number of europium 8 to 9 basically, so you can see like 2 water molecules are there. It means 6 sites are getting replaced by ligand. And from computation, hyper computation, we got the ML3. So it means this ligand is working as bidentate ligand. Same thing is applicable for 3,4-PDCA. The lifetime experiment suggested bidentate coordination of both 2,3-PDCA and 3,4-PDCA. And if you see the value of stability constant, so value of stability constant basically decreases. These are the stepwise stability constant on successive complexation. So why it is so? So we have speculated that on successive complexation, there is a steric congestion because these ligands are quite bulky and hence this trend. And one more thing we observed that the log K value of europium 3-PDCA complex is higher than europium 3-PDCA complexes, and also ML3 is not formed in case of europium 3 or PDCA. It means complexation mode is different in both the complexes. And these are the possible coordination modes one can expect in case of europium 2,3-PDCA. So these are the bidentate as proved by lifetime measurement. So in case of 2,3, one possible mode can be like one nitrogen and one oxygen of carboxylates, or both the oxygen of carboxylates. While in case of 3,4, only this possibility is there. And then again, we have used linear free energy relationship plots. So what I have done here, I have collected different data from the literature, and this plot is basically the linear plot is for europium monocarboxylate. This plot is basically for dioxygen, and this top plot is for europium aminocarboxylate. One can see the data of europium 2,3-PDCA fits in the plot of europium aminocarboxylate, whereas the data of europium 3,4-PDCA fits in the plot of europium dioxygen chelate. So what does it mean? So it means the bonding in case of europium 2,3-PDCA is through one nitrogen atom of the ring and one oxygen atom of the carboxylate, and not like both the two oxygen atoms of the carboxylate like in case of 3,4-PDCA. Then we have optimized the geometries and for both the complex. So here I have shown only for europium 2,3-PDCA with different modes. So these are the geometries if I consider one oxygen, one nitrogen, and here I have considered both the oxygen of carboxylates. And here I have shown in this table the bond lengths basically. So important thing to notice is that as complexation is there, as complex is forming like from Ml, Ml to Ml3, there is an increase in the europium O, and this O is of water. So it means water is getting repelled from the coordination sphere as ML3 is forming, and it is obvious basically because of steric regions, it is the bond length is increasing. And we have calculated complexation energy also. So here I have shown, here I will show only for europium 2,3-PDCA, assuming this bidentate mode where N of pyridyl and O of one carboxylate is forming. So here you can see in case of ML3 basically this is more stable compared to this. So this also basically theory also tells that yeah, this complex is more stable or this body is more stable. Now I will conclude my talk. So the problem of poor luminescence can be eliminated by selecting or by choosing the different efficient ligands using ligands like fluorescence. And in our laboratory, parts per trillion level of detection has been achieved in aqueous medium using efficient ligands and synergistic agents. And luminescence spectroscopy is an excellent tool, particularly in solution where you have low concentration of europium. And these theoretical calculations provide the understanding of complex formation at the molecular level. And these facilities basically we have, so we have Edinburgh spectrophotometer. So this is for students, suppose somebody wants to use our facility, so we can go to 22 nanometer, lifetime picosecond to seconds. We have liquid nitrogen DVR because phosphorescence generally you cannot record at room temperature. So you have to cool the system. So we have this facility. Also we have some protonation software like hyperspec program to calculate stability constant and species and steady. And we have DFT computation package like Gaussian and Corba. Thank you very much.
Thank you, Dr. Kumar, for a nice presentation and finishing in time. Now, yeah, please.
Yes. We have looked at the enhancement of the fluorescence by pushing away the water molecules by adding ligands and sometimes the synergistic agents. I'm curious to know what would happen if you replace water by other solvents like acetone or dioxin or aspirin. They are all equally polar, but they may have different effect on the excitation.
And even if you see my PhD thesis, I have basically explored different solvents in order to see if we can sensitize fluorescence. So for example, acetonitrile I have used in my PhD thesis.
So I have observed, for example, in water medium, this complexes will be limited like ml or maximum ml2. But in acetonitrile, where you have like non-polar or slightly polar solvent, so I observed that high stoichiometry complexes are.
No, that's right. That is regard to complex one.
Yeah.
I'm asking about fluorescence enhancement.
Yeah,
Does
fluorescence-
it get enhanced if you replace water by a solvent of lower dielectric strength,
Yeah,
like acetone or?
So deactivation part is getting reduced, but only thing is that extra channels from where you want to transfer energy, that part you have to add. So definitely lifetime is going up. Even D2O, you can use D2O, H2O to D2O if you see lifetime 110 to 1000 microsecond, and 10 times enhancement is there.
So Satyendra, nice talk. And you have shown one empirical equation where you have connected the number of water molecules in the hydration field and the lifetime. But in that lanthanide series, the number of water molecules per meter, mostly 9, and then after gathering,
Yeah, 8.
8. So then does that equation make sense? The same lifetime, so at least after gathering.
I will get in touch. Second part.
That equation, as the coordination number is not changing,
Yeah.
then the lifetime will also not change.
No, this lifetime tells, basically this equation tells about the relationship between number of water molecules and lifetime. So if
So that means all the ions, hydrated ions, they have the same lifetime.
no, this equation is valid for only for europium. So for example, for terbium, you know
that one.
yeah. So this equation is valid only for europium. For terbium, we have different equations.
Okay.
So for all the lanthanoids, we have different empirical formula. So whatever I have shown here, it is only for.
But for European, for example, if the number of hydration water in the first 100 hydration is constant.
Yeah. Right? Yeah.
Binding energy, whatever. And is it internal energy or
It is the complex energy. So here it is not free energy, it is not delta G. Here I have not considered the entropy effect at all. So this is the absolute energy.
internal energy?
Internal energy.
Even then.
Generally, we have used the PCM model, and in our both complexes, not basically for only europium, I have done some calculation on uranium also. So uranium also we have both basically. So in case of aquacity, like 10 times less or so. So everywhere I get it. Aquacity. Yeah. This change is also we have observed. We have, so we have used PCM model. Sometimes we have used Cosmo model also.
Andrew, nice presentation. I have a question that's extension of Professor Rao's question. Like, instead of, so you have shown those ligand sensitized fluorescence, right? So like, have you ever thought about like metal-induced metal fluorescence?
Yeah, actually.
Like, if you can actually transfer the extinction coefficient to your lanthanide.
Exactly.
And just vary the distance between them.
Yeah.
So that it could actually give a much bigger number.
So exactly, if you see this, our latest publication, published in Dalton Transaction. So here we have used a quite novel approach. So what basically I have done, I have sensitized uranium, and this energy transfer is from uranium. So in this case, whatever you are telling is that so this energy transfer of europium is not directly through ligand. It is from uranium to europium. So such kind of.
And also not like a metal to metal, but instead of like a metal cluster to the metal, means lanthanide.
But
So
we have to see in solution whether such kind of cluster formation is there.
This, you could, okay.
Okay, do you have any questions from the students? Okay, if there are no questions, let's thank Dr. Kumar, and let's also want to honor him with a memento. Okay, so next speaker we have with us Dr. Ramanathan from IGCAR. Dr. Ramanathan currently head Actinic Chemistry and Separation Science section of Materials Chemistry and Metal Fuel Cycle Group. And is obtained both BSc and MSc Chemistry from St. Joseph's College, Trichy. He joined IGCAR Kalpakkam in 2002 after graduating from the 45th batch of BART Training School. He was awarded PhD in the year 2013 for the study of conformations and reactions of selected organophosphorus esters. He is also an associate professor in HBNI Mumbai. His research interests includes the development of advanced extractions that are suitable for the separation of selective separation of zirconium from metal fuel dissolver feed solutions, studies on the development of reagents and materials suitable for separation of valuable fission products such as strontium cesium from high-level liquid waste, development of novel hybrid materials such as graphene oxide, silica gel, and magnetic materials for the advanced separation studies, and development of analytical procedures for various applications related to metal fuel processing. In addition, his focus is also towards studying conformations of molecules using matrix isolation infrared spectroscopy, the effect of low temperature matrices on the stability of conformations, exotic photoproducts as a result of laser-based photolysis at low temperatures, the study of transient species using in-house fabricated electron gun assembly, the study of novel and unique unconventional weak interactions, including tetral bonding, hydrogen bonding, liquid-gen bonding, sigma stacking, pi stacking, and so on. In addition to using conventional materials like neon, argon, krypton, and xenon, quite recently, a facility for producing parahydrogen was designed, developed, and commissioned in its laboratory, which is the first of its kind in India. Currently, 2 students are doing PhD under his guidance. He has a total of about 85 international publications, 70 conference publications to his credit. Yes, Dr. Raman.
Thank you, Dr. Rudhraj, for the introduction. At the outset, I thank the organizers for giving me this opportunity. The title of my presentation is High Resolution Infrared Spectroscopy of Cold Isolated Molecules. Okay, I will continue. Even though spectroscopists try hard in achieving a good resolution, the inherent mechanisms that are operating in the molecules are responsible for making the line widths which are reasonably larger. Or in other words, the bulk phase spectroscopy, that is the spectroscopy of solids, liquids, and gases, suffer from the effects of broadening. The ultimate resolution obtained does not only depend on the instrumental resolution, therefore it depends on the nature of the sample too. Playing with the sample is a very important criterion in achieving a high resolution. And in the case of solids, since solids are bound by very strong intermolecular interaction, that leads to intermolecular interaction broadening. And in the case of liquids, the molecules collide that contribute to collisional broadening, and the gas-phase molecules move randomly that contribute to Doppler broadening. In addition, because of the finite lifetime of the exciter state, the natural broadening comes into the picture. Supposing we take the gaseous molecule and cool the gaseous molecule, and we can expect that the contribution from Doppler can be reduced. But at the same time, because we are cooling the molecules and the molecules are coming close to each other, and therefore the contribution from intermolecular interaction started rising. And eventually what we should do is the following. We should not only reduce the temperature, but also we should never ever allow the sample molecule to come close to each other. And eventually we should reduce the temperature by the addition of large amount of the inert matrix, and therefore we should cool the isolated molecule, and which is what exactly all about the cold molecule spectroscopy under isolated conditions, and which is what is referred to as the methodology of matrix isolation. Because the molecules are frozen, and the contribution from collisional, and because the molecules are isolated, the contribution from intermolecular interaction are greatly reduced, and the resultant line width is much superior in comparison to the line width of the bulk-based spectroscopy. And this is the schematic of matrix isolation setup available in our laboratory. And we have a sample mixing chamber where the sample is prepared in a typical ratio of 1:1000. And the normal inert matrices are basically the inert gases like neon, argon, krypton, and xenon, and molecular matrices like nitrogen and oxygen. In a typical ratio of 1:1000, the sample is prepared, and the sample is allowed to effuse through a high precision dosing valve. And the typical deposition rate is almost 1:1000 or even lesser. And this is deposited onto the cold cryotip, which is maintained at temperature of 10 Kelvin. And this cryo chamber, the low temperature is achieved using a closed cycle helium compressor. And a cryotip is maintained at a temperature of 10 Kelvin. And this entire cryo chamber, the sample mixing chamber, were evacuated using diffusion pump or the turbomolecular pump. And now this matrix isolated sample is ready for probing using infrared spectroscopy. For all the spectroscopic techniques, infrared spectroscopy is superior because of the absence of spectral interference, because the molecular matrices or the inert matrices are vibrationally inactive, and therefore infrared spectroscopy is superior. And this transparency shows the sample infrared spectrum of trimethyl phosphate in condensed phases, which is compared with the infrared spectrum under isolated conditions. It is clear that the line width is almost 30 wave numbers or more under in the condensed phase, where under isolated conditions is almost 1 wave number, and therefore the line width is 1 order magnitude smaller under isolated condition in comparison to the condensed phase. And here we can see that for trimethyl phosphate in nitrogen matrix, two spectral features are clearly discerned, clearly resolved. These correspond to two different conformational isomers, and because of the broadening mechanisms, we are not in a position to resolve the features in the condensed phase. In addition to the high resolution, the molecular population restricted to a few states because of low temperature, whatever we achieve. And here, not only this low temperature, but also the cage effect of the matrix operates. And this cage effect does not allow the molecular rotation, and therefore the rotational congestion is completely removed under isolated condition. And here is a comparison between HCl in the gas phase and HCl under isolated conditions. In gas phase, P and R branch lines are seen, where in the like isolated state, clear fundamental band is seen in addition to the features of the multimers, and therefore rotational congestion can be completely removed under isolated conditions. And the research on matrix isolation at IGCAR is more than 3 decades old. And it all started with conformational space and model systems such as acetals, ketols, carbonates, and lower homologous phosphates were analyzed to understand the conformations of tributyl phosphate, which is a workhorse of nuclear reprocessing. And ultimately, using these model molecules, the conformations of tributyl phosphate were unraveled. But in addition, the other high branched isomers like tri-secondary butyl phosphate, tri-amyl phosphate, tri-isoamyl phosphate also were analyzed. And the entire conformational space was understood using these studies. And gas-phase reactions are also carried out to understand the products using matrix isolation in infrared spectroscopy. The intermediates corresponding to the gas-phase reactions were trapped by not allowing the gas-phase reaction to happen, and the mechanism was established through the study. And photolysis was performed to study the exotic photoproducts through photoisomerization and photooxidation. One classic example is the cis-stilbene, where the trans-stilbene was produced out of cis-stilbene through photoexcitation, and the non-planar trans-stilbene was the intermediate of the cis to trans, and which was trapped and studied. And in addition, the photooxidation was performed using the molecular chromophores, where the molecule absorbs the light and transfers the energy to the oxygen molecule to produce oxygen atoms. And this in turn is oxygen atom is in turn is ready for the conduct of photooxidation. But in addition, oxygen molecule itself was cleaved using UV photon at 193 nanometer, and this nascent oxygen atom was like studied for the different photooxidation reactions. And recently, we commissioned electron impact coupled matrix isolation in infrared spectroscopy for the study of transient species like free radicals. But in addition, the possibility of electron bombardment to produce ozone molecule and therefore oxygen atom was tested and the resultant oxygen atom was utilized for the oxidation. And this oxidation is very different in comparison to the photooxidation, because this oxidation is produced in absence of light, and therefore this dark oxidation was compared with the photooxidation experiments. And the research on conventional interactions like hydrogen bonding is more than a century old, and we did study varieties of hydrogen bonding interactions, starting from weak to medium to strong interactions. And normally hydrogen bonding induces redshift of the proton stretching frequency. In a few cases, there is a blue shift which is observed, and the example is chloroform, and chloroform systems exhibit blue shift. And the blue shift and the reasons for the blue shift were understood using matrix isolation infrared. And halogen bonding, where halogen behaves as if it is a hydrogen atom, even though halogen is surrounded by pool of electrons, there is a positive electrostatic potential which is available, and which can act as an electron acceptor, very similar to halogen. And carbon also accepts electron, and in fact the inert atoms also accept electrons, and therefore carbon bonding, halogen bonding, all these things are studied. But in addition, the nitrogen group is a fantastic group which can exhibit nicogen bonding, very similar to carbon bonding, where it accepts electron. And nicogen bonding was studied with varieties of systems like PCl3, POCl3, nitromethane, nitrous oxide, and so on. And the decade-old problem is the structure of benzene dimer, whether it exists as a hydrogen bond T-shaped geometry or a pi-stacked geometry. And very similar to that in the case of cyclohexane, the stacking structure is possible, and we proved the cyclohexane using matrix isolation infrared spectroscopy, and we elucidate the structure of cyclohexane dimer. And the very recent one is the parahydrogen, and parahydrogen has an alternate and attractive matrix for matrix isolation because of the very many attractive properties. And we did produce parahydrogen in our laboratory, and parahydrogen production facility is first of its kind in India, and we explored the intrinsic property of parahydrogen using parahydrogen as a matrix material. And here in this talk, I'm going to make the conformational correlation of trimethyl phosphite and trimethyl phosphate. The backbone structure in both the molecules are similar, but the only difference is the extra oxygen atom which is present on trimethyl phosphate in comparison to phosphite as a phosphoryl group. But in spite of the fact that the backbone is similar, the conformational preferences are different. And the methodology in matrix isolation as far as conformational studies are concerned is the performance of the room temperature nozzle experiment to get the population characteristic of the room temperature, molecular beam experiment, and hot nozzle or heated nozzle experiment where the sample is heated before deposition to increase the population corresponding to that of the higher energy conformers, and pulsed nozzle or supersonic nozzle experiments where the conformational temperature is decreased to 100 Kelvin or so on to decrease the population of higher energy conformers and therefore increase the population of the ground state conformer. And in addition, annealing is also performed where the thermal energy is provided to the matrix, and because the thermal energy is provided, the matrix becomes soft, and therefore the interconversion process can occur to favor the population characteristic of the low temperature, and therefore annealing also can lead to the conformational interconversion, and which is what is referred to as conformational cooling. But as far as the matrix temperature is concerned, the low energy conformer only should be favored, and that is possible through annealing or through supersonic expansion. And in addition to the experiments, we also perform quantum chemical computations using density functional theory and ab initio methods using Gaussian suite of programs to corroborate the experimental results. Conformations are basically isomers which can be rotated by single bonds, and the isomerism arises when the rotation about the single bond is relatively unhindered by maintaining the integrity of the chemical structure. The simplest example we can ever think of as far as conformations is concerned is the conformations of cyclohexane, which exists in the chair form and the twist boat form. And the chair form is the ground state and twist boat form of the first excited state conformer, and the boat form is basically the transition state. And electron diffraction experiments and NMR experiments proved the existence of chair form, and thanks to matrix isolation infrared spectroscopy for providing the existence of the twist boat form of cyclohexane at high temperature at 750 Kelvin, and Chapman group of University of California provided the first experimental evidence at 750 Kelvin where the population corresponding to that of twist boat form increased to 15%. And as far as conformational stabilities are concerned, the simplest example is N-butane, where the trans form is more stable than the Gauss form because of steric effect. But in a few cases, the Gauss form will be more stable than the trans form in spite of the steric effect. One classic example is ethylene glycol, where hydrogen bonding is present only in the Gauss form and therefore is more stable than the trans form. But in the case of cyclic system, hyperconjugative interaction is operating, and the classic example is sugar, where normally in the cyclic systems, because of 1,3 axial steric interaction, the axial preference is not at all preferred. But in the case of sugars, axial conformer is more stable than the equatorial conformer, even the steric effect is present. That is simply because of the fact that the hyperconjugative or anomeric interaction in sugars is called as an anomeric interaction, and that is basically the delocalization interaction. In valence bond theory, it is called as a no bond double bond resonance. In molecular orbital theory, it is basically electron donor acceptor overlap. And in the case of acyclic systems, this is transformed as a gauche effect, wherein only in gauche conformer this hyperconjugative effect is operating, and which is more stable than the trans conformer. There are two kinds of hyperconjugative interactions. One is vicinal, the other one is geminal. Vicinal operates in four-centered system, and geminal operates in three-centered systems. Both contribute for the stability of the conformers. And this is all about the conformations of trimethyl phosphate, which was studied in our laboratory. And this spectrum is basically the trimethyl phosphate spectrum under isolated conditions at 12 Kelvin and nitrogen matrix. And this is at a high temperature, that is a high temperature of 32 Kelvin. And the potential energy surface of trimethyl phosphate reveals two conformers. One is gauche with respect to the, where all the methyl groups are oriented gauche with respect to the phosphoryl group. This phosphoryl group is the reference. In the higher energy conformer, one of the methyl groups is oriented trans and the two methyl groups are oriented gauche. As I said, only in the gauche conformer, the delocalization is possible, and therefore the number of such hyperconjugative interaction is more in the case of gauche than in the case of trans, and therefore the gauche is more stable than trans by 0.9 kilocalorie per mole. And therefore the room temperature population contains both this gauche and trans conformers with the population of say 59% and 41%, and the immediately deposited trimethyl phosphate in nitrogen matrix reveals that the population is exactly similar to the theoretical prediction. And at high temperature, it can be seen that there is no change in the conformational population at all, and the conformation is conserved, population is conserved at high temperature, simply indicating that the equilibrium vapor phase population is becoming a non-equilibrium matrix population in the matrix that becomes the non-equilibrium population forever. But the conformations of trimethyl phosphate in xenon matrix is very interesting, because as a function of temperature, you can very clearly see that the contribution from the higher energy conformer started decreasing, and at a high temperature of 60 Kelvin, and this completely disappeared to form the ground state gauche conformer. This indicates that the equilibrium vapor phase population becomes a non-equilibrium matrix population at low temperature. But because of the accessibility of the very high temperature, this non-equilibrium population becomes an equilibrium population. And in addition, the xenon matrix also offers a higher substitutional cavity, and therefore this population in interconversion happens. And the interconversion barrier was calculated to be 1.4 kilocalorie per mole, which could not be achieved in nitrogen matrix because of low annealing temperature, but which is possible in xenon matrix because of the higher annealing accessible temperature. For trimethyl phosphate, as I indicated, even though trimethyl phosphate is very similar to phosphate, the conformational preferences are very different. The trans conformer, which is the highest energy, which is the first higher energy conformer in phosphate, turns out to be the ground state conformer, and the ground state gauche conformer turns out to be the highest energy conformer with no experimental significance, right? And that is simply because of the fact that in trimethyl phosphate, the oxygen lone pair gets delocalized to the delocalized to the phosphorus to create a partial double bond character, and which is possible only when one of the methyl groups is oriented trans. In the gauche conformer, since there is no methyl group which is oriented trans, and this interaction is completely absent, and that is the reason why it is kept fourth in the energy ladder with no experimental significance. And the population corresponding to the ground state is 85%. There are two conformers whose population contribution is 15% to room temperature, and the experiments were performed where nozzle was used at room temperature and high temperature, and also pulse nozzle experiments were done. And the infrared spectra look exactly similar in all the cases, simply indicating that there is no population contribution from the higher energy conformers. And what happened to the higher energy conformers? And the calculation revealed that the barrier is very, very less. And because of the small barrier during deposition itself, this higher energy conformer gets interconverted to the ground state conformer. And that is the reason why the equilibrium population is achieved in the matrix. And therefore, this is one of the classic examples where equilibrium vapor phase population become the equilibrium matrix population forever. And this is the conformational correlation of phosphate and phosphate. As I said, trans is the ground state conformer for phosphate, and gauche is the first highest energy with no experimental significance. And the same gauche is the ground state conformer for phosphate, and trans is the first higher energy conformer. Supposing I convert this trimethyl phosphide to phosphate by just doing the photooxidation of phosphide, then I will be converting the trans conformer of phosphide to phosphate. And now this trans conformer is not the ground state conformer of phosphate because it is the highest energy, the higher energy conformer in phosphate. And therefore, I can produce an equilibrium population that is which is far from equilibrium, and that is what is performed. And the photooxidation was performed using UV laser photon, using 266 nanometer Nd:YAG laser as well as the broadband source. And it revealed that the trimethyl phosphate is produced out of photooxidation, and the population corresponding to the higher energy trans conformer. You can see here that is basically the broken spectrum, which is much higher than the population whatever is expected from the normal trimethyl phosphate molecule, which is directly deposited onto the low temperature matrix. And therefore the population is far from equilibrium, and that is only because of the fact that the trimethyl phosphate to begin with is existing in the trans conformation, which is the first higher energy conformer as far as trimethyl phosphate is concerned. But in addition, there are other features which cannot be explained for the other molecule which can be formed. And therefore, overall, the cage effect of the matrix plays an important role in preserving the non-equilibrium population, because cage effect is operating under low temperatures. At low temperatures, non-equilibrium conformational population of molecules during their in situ production. And the other important matrix, whatever I said, was parahydrogen is attractive for so many reasons. For want of time, I'm not describing in detail. But very important thing is parahydrogen is a quantum crystal because of its small mass, and it has a large amplitude 0-point vibration, and therefore a self-repairing mechanism of the site effect is operating at low temperatures. And we explored the property of parahydrogen, and this is basically the trimethyl phosphate spectrum in argon and krypton, which is side split. And one of the important problems in matrix isolation is the side splitting. The same frequency will be split into many. But in parahydrogen, because of the quantum crystal nature, the side splitting is very less. And we have a parahydrogen production facility, and parahydrogen is basically the spin isomer of hydrogen, which is a consequence of Pauli's exclusion principle. J is equal to 0 rotation state corresponds to para, J is equal to 1 corresponds to ortho. Even though ortho is higher energy form, because of the degeneracy, ortho form is having 75% population in comparison to the para form, which is 25%. And parahydrogen is very attractive because parahydrogen does not have any nuclear spin, and therefore it can provide an interaction-free environment for the guest molecule. And therefore parahydrogen has to be produced, and therefore we have to lower the temperature, and we have the parahydrogen production facility, and these are all the photographs. I'm not describing in detail. We did produce parahydrogen with a purity of 99.3%, and parahydrogen production facility was commissioned when Dr. Vasudeva was the director of IGCAR. And this is the characterization of parahydrogen to begin with using Raman spectroscopy in the gas phase. And this is basically the comparison of photolysis of phosphite, basically nitrogen and parahydrogen matrices. It is very clear that in the case of nitrogen matrix, as I already indicated, the population of trans is very high in comparison to that nascent phosphate. But in the case of parahydrogen matrix, it is very clear that this is the one which is produced out of phosphite, and this is basically the normal phosphate in parahydrogen matrix. And here there are no additional features whatever we are seeing in the case of nitrogen matrix. And here there is a comparison, and this additional feature is not present, and these features are not at all present in the case of parahydrogen. But in addition, you can see that the population characteristic of the trans conformer is slightly more than the population corresponding to that of normal trimethyl phosphate in parahydrogen matrix. This implies that the quantum crystal of nature of parahydrogen plays a very important role, and because of this large amplitude 0-point vibration, and because of the quantum crystal nature of parahydrogen, the near equilibrium population of trans is produced in the case of parahydrogen, unlike the case of the trimethyl phosphate photooxidation in nitrogen matrix. And therefore, overall, the equilibrium vapor phase population of trimethyl phosphate became a non-equilibrium matrix forever in nitrogen matrix. In xenon matrix, that became an equilibrium population because of the larger, the accessible temperature of xenon. In phosphate and nitrogen, an equilibrium vapor became an equilibrium matrix because of the low barrier of interconversion. And in TMP produced through photooxidation in situ using phosphite, revealed that the equilibrium vapor of phosphite became the equilibrium matrix for trimethyl phosphate, and which became a non-equilibrium matrix in nitrogen matrix far from equilibrium. And in parahydrogen matrix, it's basically a near equilibrium population because of the quantum crystal nature. And therefore, the conformations of trimethyl phosphite and phosphate were analyzed using matrix isolation in infrared spectroscopy. The conformational correlation was accomplished through the photooxidation in nitrogen matrix. And the intrinsic nature of parahydrogen was established using in parahydrogen matrix through photooxidation route. And overall spectroscopy of matrix isolation is a powerful tool because we can study, because studies on molecular structure is important for understanding varieties of chemical, physical and biochemical processes. Spectroscopy of matrix isolation provides us with better insights into the molecular structure. And I would like to acknowledge Dr. Shivaraman, director of our group, and Dr. Vijayaraman, Associate Director for all the moral support and encouragement. I did all the experiments with my colleague, Dr. K. Sundarajan and Dr. K. Shankaran, who is a former colleague. And I thank my mentor, Professor K. Vishwanathan, a former professor of Aizer Mohali, for all the support. And everything happens only because of the research scholars. And I thank research scholars. And these are all the publications in the year 2017 to 2022, almost 35 publications we have. And I complete my talk with the quotation of two Nobel laureates. One is Francis Crick, who is a Nobel laureate in 1962. Almost all aspects of life are engineered at the molecular level. And without understanding molecules, we can have a very sketchy understanding of life itself. And Wolfgang Pauli, who is a Nobel laureate in 95, said somewhat opposite, as the best that most of us can hope to achieve in science is to simply misunderstand at a deeper molecular level. In either way, scientists do enjoy the fruit at the end of the day. Thank one and all. Thank you very much.
Ramanathan, for a nice talk. Yes, the session is open for discussion.
Thank you, sir. Regarding matrix isolation, have you looked at some isolation of some or observation of unusual main group metal species?
So main group means
it was any silicon, low valent silicons or such species.
But in terms of species, in terms of
matrix isolation observation.
Look, in terms of metal,
silicon dihydride.
But that can be done in principle. Okay. And we have done silanes where we deposited silanes.
Okay.
But in principle, matrix isolation can be coupled with the laser ablation where we can produce the species of your enter. For example, if you want to produce silicon oxides and you can ablate silicon because oxygen is always present as an impurity and therefore silicon oxide will be produced. And therefore the various species can be produced through matrix isolation via laser ablation.
What are the conditions this matrix isolation? Conditions?
But conditions in the sense we can analyze the liquid gaseous molecules. Basically, it is a mixing of gaseous molecule with the matrix. For example, I want to study the acetylene. Acetylene can be mixed in a typical ratio of 1:1000 with respect to matrix. And matrix can be argon or nitrogen, and then it can be deposited, right? But supposing the sample is a liquid, then I can take the desired vapor pressure at a room temperature, at a desired temperature in a typical ratio of 1:1000 again, and I can deposit. And supposing the molecule does not have a vapor pressure, and the vapor pressure is 10⁻⁻5 millibar, right? I cannot prepare 1:1000 because the vapor pressure itself is 10⁻⁻5 millibar. But still it is possible where instead of static loading of the sample, static mixing of the sample, we can dynamically expand the sample. Along with the matrix, the sample can be expanded and the sample can be deposited, and therefore even solid molecules also can be studied if the vapor pressure is in the range of 10⁻⁻5 millibar or even less. But we can do varieties of things. We can do laser ablation and we can couple electron bombardment where we can produce transient species and so on.
I have some more questions, but I will discuss in
definitely.
Lunchtime. Thanks. I have
Yeah, but it's in situ. That is, phosphate was deposited into the matrix along with oxygen, right? And then it was irradiated. That is like using normal broadband photolysis source or laser source. And then in situ, phosphate was produced. Phosphate was produced in situ, and it was compared with the population of phosphate which is directly deposited. But imaging, so you are talking about the IR imaging.
Yeah, localized.
Yeah, that definitely that can be done, but we are not doing. Actually, that will be very, very interesting. But through matrix isolation, we cannot like mimic whatever condition you are saying. That is, I want to I want to study the surface morphology of the molecules, but it is absolutely difficult. But through IR imaging, it is possible.
Any questions from the students? Yes.
Good morning, sir. To know, so since this technique seems heavily dependent on what matrix you're choosing, so what are the like general criterion for choosing a matrix? Like what do you look at in a molecule?
Yeah, because we are probing using infrared spectroscopy, and obviously we will be looking for a matrix which is IR inactive, right? And therefore we are using all inert matrices like neon, argon, krypton, and xenon, right? And it is infrared inactive, and the nitrogen and oxygen matrices are infrared inactive, and therefore these matrices are preferred. In principle, you can do studies with CO2 matrix also, but the problem with CO2 is CO2 is IR active, and therefore you will be getting a, because the amount of matrix whatever you are depositing is very, very high in a typical ratio of 1:1000, and therefore the amount of CO2, supposing you use CO2 as a matrix, will be very, very high. Supposing you have signature vibrational regions in the CO2, in the region where CO2 is absorbing, then you will be losing the information, and therefore it is all the time preferred to use a matrix which is not giving any spectral interference.
Can you repeat, like, since you even within noble gases you have 2 or 3 types, so you check in each, and each affects whether you're getting an equilibrium or a non-equilibrium. So do you do every sample and every matrix, or is there a way of choosing things for specific experiments?
No, repeat.
I mean, like doing something in a nitrogen matrix is giving you, say, a non-equilibrium population, but doing the same thing in xenon is giving you an equilibrium population.
Yes, yes.
So do you repeat all your experiments in each kind of matrix to?
Yeah, definite. Actually, first I do the experiments in nitrogen matrix. I study the properties thoroughly, and then I change the matrix. And for example, nitrogen first and then xenon next. And not only xenon, we did perform in krypton and argon matrices where the conformational profile is totally different actually. And different matrices will be different, will be tried in different occasions, and then the population analysis will be performed.
Thank you.
Okay, so I have one question. So this is regarding your calculation. So you define your equilibrium, non-equilibrium based on your gas-based calculations.
Yes.
But however, you are doing the experiments on a matrix isolation technique.
Yeah, actually,
So, yeah.
Finish it.
The point is that how valid is this?
No, actually,
Technically, I would expect to do these calculations within the nitrogen
we do
matrix.
perform calculations under continuum model also. That is where we try to mimic the dielectric constant of, we try to introduce the dielectric constant of argon, krypton or xenon, and then we do calculations that corresponds to like which corresponds to the dielectric constant of the matrix. But majority of the times, the calculation whatever is performed in the gas phase will be closely lying with the experimental the population or feature whatever we are getting. But still, like calculations are performed like with the like where the effect of matrix is taken into consideration.
Okay, if there are no more questions, let's thank Dr. Ramanathan.
Thank you very much.
Let's give him a memento. Next, we have Dr. K. Dubey. Dr. Dubey is working as a scientist in Radiation Technology Development Division at BART. His research interest includes the radiation processing of polymer blends, alloys, and nanocomposites for advanced applications. Presently, he is engaged in radiation processed biodegradable polymers over current protection devices, strain sensors, toxic volatile sensors, and high modulus nanocomposites. He has about 75 publications in international journals and more than 50 contributions at conferences and symposium. Dr. Dubey.
you very much, Mr. Chairman, and a very good afternoon to you all. I'm going to discuss some important applications of radiation technology. So in this talk, I'm going to give you a brief context of what do I mean by radiation processing. Then I will quickly go through some of the established applications of radiation technology. And finally, if time permits, I will glance through some latest sensors and conducting composites that we have developed. So radiation is a very broad term. It encompasses entire electromagnetic radiation. And if we believe de Broglie, then all particles moving in the medium are also constitute radiation. So let us define what do I mean by radiation here. Here we are talking about high energy radiation. Typically, this radiation has energy more than 1 million electron volt. And what is the typical bond energy? That is few electron volt. So really we are dealing with very, very high energy radiation. So we deal with X-rays, gamma rays, electron beams, and other particles which are in MEV or high keV region. Now, what is your guess? When such high energy radiation will fall on a material, what will happen? Whether it will become radioactive, whether fire will start, or whether it will burn. Obviously, energy is very, very high. To your surprise, most of these changes can be utilized for developing several useful products. And radiation processing today is a multi-billion-dollar industry. It is utilized in case of healthcare, environment, food, and agricultural application. Let us see how. So when we are giving high energy radiation to the material, of course, energy is very, very high. So ionization will take place, and you will get one radical and one energetic electron. As we know that radicals are very reactive in nature, and so is this free electron. We utilize radicals and electrons to undergo different kind of radiolytic reactions for different kind of applications. So for radiation processing, generally high molecular weight entities or molecules are very efficient. So high molecular weight entity, you can say nucleic acids, DNA, proteins, and even synthetic or commercial polymers. So medical sterilization, if you see, medical sterilization is an example in which radiation is used to kill pathogens or germs in the medical product. Most of those products are processed by high energy radiation. And in radiotherapy also, in radiotherapy we use radiation to kill, to damage the DNA of the tumor cells. Here I will be talking about synthetic polymers. And when you irradiate any synthetic polymer, what kind of changes are going to take place? If you see the right side schematic, after irradiation, a lot of radicals will be generated on polymer chains. There are three important possibilities. Either those radicals will recombine with each other, or if recombination is not possible, chains will break, or if these radicals are exposed to some monomer or some reactive species, they can initiate some polymerization reaction. The first process is called cross-linking. The second process is called degradation. And the third process is called radiation-induced grafting. All these processes have many applications of industrial significance. Now, what is cross-linking? Cross-linking is forming linkages between two polymer chains. To give you an example, you can have random pipes. And if you join two pipes, you are going to get a ladder. If you join multiple pipes, you can get a scaffold, which is going to have very high strength. So in case of radiation cross-linking, we are making those kind of linkages at molecular level. You can imagine that what kind of improvement it is going to give in terms of mechanical, thermal, and chemical characteristics. So I will glance through some of the applications of radiation technology. Radiation cross-linking is widely used to produce high-quality wires and cables. Now, on the right side, you can see there are two wires. One, the back wire is made from conventional processes, and the forward one is made from using radiation cross-linking. When we are passing similar current through both the wires, you can see that the conventionally processed wire is starting to getting fumes. And after some time, you can see that the pipe is completely getting nuded, whereas radiation processed wire is completely intact. The reason is in the basic mechanism by which radiation cross-linking works, it allows preservation of constancy of the polymer, at the same time linking the amorphous domains. That's why the mechanical properties and the current carrying properties all are very advanced in case of radiation processing. Radiation processing can be used for the development of heat shrinkable tubes. Heat shrinkable tubes works on the concept of memory effect. Most of the polymer remembers under which conditions they were irradiated. So you irradiate them, then you can give any other shape, and when you apply heat again, they will regain their original shape. Now, this is a phase therapy mask that we have developed for radiotherapy application. As you know that in case of radiotherapy application, a patient is subjected to gamma radiation or high energy radiation to treat the tumor. Now, during this application, we have to immobilize the face of the patient. Now, every patient has different kind of facial contours, and we cannot apply plaster on the face of the patient. So these shape recovery polymers we have developed, these things can be stretched to whatever dimension we want. They can be applied on the face of the patient, and when the job is done, if we put them in the hot water, the original shape will be regained. These are another example of shape recovery polymers we have developed. So they retain shape for more than 1 year. For example, the sample has been deformed to 90 degrees, and it retains shape more than 1 year period. And the moment it is heated to the desired temperature, it regains its original shape. Similarly, we have those applications in which we have to apply temperature. Here we have developed another system in which shape can be recovered by applying by applying certain voltages. Hydrogels is a well-established example of radiation processing. It contains more than 99% of water. These are used several medical applications for treating diabetic foot ulcer and chronic wounds. Radiation can also be used for producing high-quality polymer foams. Tires. Most of the advanced countries use radiation-processed tires. In India also, now industries have started using electron beam processing for developing high-strength tires. There are several other applications in the automobile area. Radiation cross-linking is also used for development of resettable fuse. You know what is the function of fuse and MCB? Whenever current is passing through a certain value, it should stop the flow of current. Now, in case of advanced electronics, etc., we have developed, or in fact, commercially it is used, resettable fuse. Whenever current increases a certain value, it will not allow flow of current. Another important technique is grafting. In radiation grafting, what we do, we take one polymer, irradiate it, radicals are generated on its surface, and then we incorporate different functional groups on its surface. Now, depending on the application, you can make ion exchange resins, you can make antibacterial substrated, you can make battery separator, and there are multiple applications for this. This is one of the applications which we have demonstrated at industrial level. As we can see, the textile industry is highly polluting. We have developed a grafted matrices which can treat textile wastewater. These pilot scale plants are being tested at in different dye industries now. This is another example in which we have developed a dye adsorbent by using radiation grafting. It is having very high dye adsorption capacity, more than 1,000 milligram per gram. So, as I told, that grafted matrices can also be used for the development of antibacterial dressings as well as battery separator for different batteries. Radiation degradation also has many applications. Now, this is one application in which natural polymers, for example, chitosanol, alginate, etc., they generally undergo degradation on exposure to radiation. After radiation exposure, if we spray these polymers to plants, they elicit plant growth activity. So we have conducted large-scale plant trials on different crops, particularly on the mint crop, and we have demonstrated not only growth kinetics, plant growth has become faster, but the product yield or plant yield is also higher. By using radiation degradation, PTFE can be converted to PTFE micropowder, which can be used as a dry lubricant in different kind of applications. Radiation can also be used directly to decolorize as well as demineralize dye waste.
Now, if you see in last few decades, the human population has increased by manifold. So is the human waste. Now it is very challenging how to take care of this human waste. Human waste has lot of pathogens and they are not suitable for agricultural application. To make the process sustainable, whatever we are taking from plant, it should be given back to the plant. So in BARC, we have developed dry sludge sewage hydrogenation technology, in which we take sludge, we use high energy radiation to kill certain level of pathogen. As a result, foul smell comes down, foul smell goes, as well as bacterial level comes down to the level by which it can be handled safely by farmers. So currently, then we inoculate this hygienized sludge by some friendly bacteria, and this is marketed as a fertilizer to the farmers. It has several advantages. It kills weeds, it reduces odor, it reduces vector attraction, etc. Now this is a presentation from Ahmedabad Municipal Corporation, which is the first plant established using this dry sludge hydrogenation technology. You can see that the process is very simple. Dried sludge is crushed and put into tote boxes. Then cobalt-60 radiation is given. Then NPK fertilizers are added to it. And then finally it is sealed in bags, and sometimes it is mixed with urea, and sometimes it is used directly as a fertilizer. Now currently in India, there are many places in which these plants are coming up. It is coming up in Pune, Surat, Vadodara. We already have Ahmedabad. It is already working, and in Indore also it has got commissioned. Now I will quickly go through some of the sensors that we have recently developed. Now these sensors will be used to mimic our senses or to detect the responses from our sensory organs. So we can see we have different kind of sensory organs. We have different kind of senses: smell, touch, taste, vision, and hearing. These senses does not have any purpose except some evolutionary purpose to protect us from some foul smells, etc. But in today's time, when use of prosthetics as well as bionics is going to increase, there is a requirement to develop those sensors which can replicate the response of our sensory organs. For example, if artificial hand is put to a human being, he will completely lose the sense of the touch. If we can provide artificial skin, then the sense of touch will be regained. And the same thing goes for smell, taste, as well as other kind of sensors. In case of robots also, it is desired that they should also be getting human feeling. So these sensors are going to have applications in robotics as well. And finally, which is the immediate effect, is to develop different kind of sensing arrays which can detect disease at much advanced stage, at much earlier stage. So I will be giving you two examples. One is related with odor sensors or artificial nose applications. We are developing these sensors by using quantum tunneling concept. So what we generally do, we take a polymer matrix and we take a conducting filler. We make sure that they are close to the percolation threshold. When things are at the percolation threshold level, there are two kinds of electronic conduction in the matrix. One conduction is directly between the metallic nanoparticle, and one conduction is through the polymer phase. This is governed by tunneling conduction. It is because of the tunneling of the electron. So if we make any, and this typical distance is only 20 nanometer. So if my polymer matrix is responding to any analyte, and if it is producing any change in this 20 nanometer region, I can develop a sensor. So this is a simple concept that is used. But for this, the interfacial characteristics have to be well defined. Chain entanglement has to be controlled. Morphology has to be well defined. As well as if we are using AC voltage, then frequency dependence also has to be conducted. Now this is one example of the sensor that we have developed, aromatic compounds. So they are known for their strong smells. So we have taken benzene, toluene, ethyl benzene, and xylene. You can see their structures are very quite similar. So the sensors that we have developed, you can see that they are showing response to all. benzene is having the highest response, and xylene is having the highest response, and benzene is having the lowest response. So we have developed a sensor, but you can also notice that all these sensors are showing response to all the analytes. Though the magnitude is different, but the sensing response is shown to all the analytes. Now, whether it is an advantageous situation or it is a disadvantage for us, we have to see in our own sensing mechanism. How many olfactory sensors or how many neurons do we have which have distinct response to different kind of smells? So currently there is an estimate that humans can distinguish more than 1 trillion scents. And traditionally it is known that we can have 10 basic categories or fragment that we can detect. So do you think that we have 1 trillion different kind of sensors for detecting individual smells? No, it does not work in that way. Our brain works in terms of identification of pattern. We remember pattern and then those patterns are decoded. So by using these sensors, I constructed an array of 4 elements in which different amount of carbon nanotube and graphene are used in the same polymer matrix. And then I applied principal component analysis. You can see that I have been able to resolve the response of all these analytes. Now currently we have developed much more advanced sensors which are giving even better results. This is the sensor that we have developed. It's for acetone. Acetone is a marker for different kind of diabetic diseases, and you can see that this sensor is highly selective for acetone, and almost there is no response for methanol, ethanol, and other kind of gases that are typically present in our breath. Finally, we have shown that all these sensors, the sensitivity of these sensors can be enhanced by giving particular amount of radiation dose. And this is because the radiation is selectively modifying the interface of carbon nanotube and polymer. We have recently developed a sensor for ammonia in which we have developed a new process in which carbon nanotube is inducing percolation in the natural rubber latex. So as a result, we have developed a sensor for isoprene. Isoprene is again a biomarker for several kind of disorders. Then this sensor we have developed by using a conducting polymer, polypyrrole. As we know that polypyrrole or all conducting polymers are very promising, but their mechanical properties are very poor. So here we have utilized the concept of radiation grafting. First we have grafted acrylic acid on a substrate, then we grown polypyrrole on its on the top of it. So the lower profile you can see that after grafting and we have done this tape addition test. You can see that after grafting nothing is coming out. So the entire polypyrrole is intact. The matrix is completely conducting. Whereas if I try simple the same thing without grafting or on any other substrate, you can see that polypyrrole will be completely peeled off from the substrate. Now this sensor is highly specific to ammonia. So what are we trying to do? All these sensors are not already available. Now, if you must be aware that electronic nose is a quite popular concept in the area of food technology, but they are generally using TCMS, which is not only expensive, it is quite bulky. So suppose I have to make a electronic nose which has to be implanted on a human being. I need very miniaturized sensors which can be placed and integrated with the human body. So the sensors that we are developing, they are presently, because of our electronics limitation, are having few dimensions. And now we are working on getting them to the micron level. I will give you just few examples, one example of the sensors that we have developed. Now in the case of this tactile sensing, we want stretchability, we want self-healing characteristic, as well as these things should be biodegradable also. So this is one of the important sensors that we have developed. You can see that the sensor dimension, it is on the tip of the finger. The dimension is only 4 mm. This sensor can detect load up to 1000 Newton, which is around 100 kg in a reversible way. There is no need of any external electronics. We just need power supply and we can connect it to the LED. By the intensity of LED, we can find out that what is the application of the load. Okay, so these things can be directly integrated with any kind of circuit. And you can see that the response is instantaneous whenever load is applied, and it comes back to its almost original position once the load is removed. So for our military applications, some devices are being built based on this concept. Finally, this is an example which shows the sensor response. The sensor is placed on the finger of one of our colleagues, and he's flexing his finger. You can see that the sensor response is reproducible. Whenever he's flexing his finger, sensor response is there. And those responses further we have validated by using electromechanical analysis. It can withstand up to several thousands of cycles. And on the right bottom corner, there is a two-dimensional array that we have constructed for tactile sensing applications. So you can see that when we are putting one finger, there is one dot. When we are putting two fingers, then there is two dots. And this is the final slide. This is the self-healing characteristic of the sensors of the matrices that we have developed. You can see that these are polymethyl methacrylate and poly N-butyl acrylate copolymers, and we are measuring the self-healing characteristics. So as we are increasing the concentration of N-butyl acrylate, self-healing behavior improves. So you can see it is recorded as the function of time. When N-butyl acrylate is 60% on the top one, and when it is at the 45%, you can see that whatever cut that we have put a cut on the matrix, and then we have examined its recovery under a microscope. You can see that when N-butyl acrylate is 45%, the recovery is not complete. When we increase the fraction up to 60%, you can see the right profile that the wound or whatever cut we have made, it has been completely recovered. So finally, I will conclude that radiation can be effectively used to modify the interface characteristic of polymer nanocomposites. The need is to carefully tailor the interface region. Smart tactile and VOC sensors can be developed using radiation technology. Finally, I would like to acknowledge all of my colleagues, organizers, industrial partners, and other collaborators. And finally, thank you very much for your kind attention.
Thank you, Dr. Dubey, for a nice talk. Your session is open for discussion. Yes, Peru.
Nice talk. I'm just curious to know about your the scent sensor. Where do you have application that one?
So the current application is in the diagnosis. Means, for example, one particular condition is diabetic ketoacidosis, in which the ketone level or the acetone level from our breath becomes up to 1000 ppm. Now, current test involves 24 hours biochemical estimation, etc. Now, this sensor can be directly put on the mouth or through breath. The examination can be done. Likewise, the other sensor is for lung cancer that we are trying to develop in cooperation with the relevant experts. So there are some markers. For example, toluene is higher, isotonic is higher if a patient is going to have lung cancer. So this is the basic idea of having those sensors.
Okay, thank you.
Dr. Dubey, it was a very interesting talk. Just have one doubt. When you make these polymers by radiation, what is the probability that the product you make every time is similar? Because the interaction is going to be probabilistic. How sure you are that the product is same? Because you have properties for a given product, is it not? Am I, is that, yeah.
No, that's very valid. So polymerization itself is a probabilistic thing. So you use any process, whether it is radiation or otherwise, you are always going to get a distribution curve. But that distribution is reproducible. So whenever we are trying to develop any new system, we determine its molecular weight distribution or whatever parameter we are trying to see, and that remains consistent.
Okay, if there are no more questions, let's thank Dr. Dubey. On behalf of the organizing committee, I want to give him a moment. so next we have next speaker is Dr. Sri Ramamurthy. Dr. Sri Ramamurthy completed MSc from Andhra University, Visakhapatnam in 2006 and joined BARC as a trainee scientific officer. After completion of the 50th batch, 3 years training at BARC, he joined IGCAR Kalpakkam 2007 as scientific officer. He pursued PhD in chemical sciences from IISc Bangalore in 2017. He is also an assistant professor at HBNI. His major research interests include semiconducting metal oxide synthesis, characterization, and studying the application towards gas sensing, application of multivariate analysis tools to process the sensors data, and development of solid electrolyte-based potentiometric sensors for liquid sodium application. He has about 17 publication peer-reviewed journals, about 20 national and international conference proceedings, symposia, and spirit. He is a recipient of the Young Researcher Medal of the Society of Material Chemistry for the year 2021. He is a life member of the Society of Advancement of Chemical Sciences and Education, the Society for Material Chemistry. He takes keen interest in various SASC-related activities in delivering lectures, conducting quizzes, demonstrating experiments for students at different levels of schools, colleges, and universities in South India.
Thank you, Chairman. And the outset, I thank organizers for giving me this opportunity to present a brief introduction to chemical sensors, necessity and challenges. So I work in novel chemical sensors section of Material Chemistry Division in IGCAR. And in this particular presentation, I'm focusing for the student basically. So the interest is to introduce the subject of chemical sensors. And I thank Professor Dubey. He already introduced us in a little bit. I will be continuing in different line. So the plan of my talk is only a basic terminology introduction and necessity in various fields, how chemical sensors are useful in different areas. And also, what are the challenges involved in the development of chemical sensors? And I finally will come to. And moreover, any chemical sensor market, if you see over the period from 2018 to 2030, the expected growth rate is 7.1%. So it's keep on increasing. So in 1960s, Professor Taguchi introduced the gas sensors, and the market is ever increasing so far. And why it is so? So the chemical sensor, basically the technology from the definition, it is a device that transforms chemical information ranging from concentration of a specific sample component to total composition analysis. This is the ideal definition given by IUPAC for the chemical sensor. So basically the sensor will have different components. It will have a recepting element or receptor layer where the analyte species will interact with that, and it undergoes some physicochemical change. And that change has to be transmitted to the transducer, and the transducer converts that change into electrical signal, which can be read out by the instrumentation, and finally you can read what are the changes that happens. So that is what the sensor works. So these, whatever the receptor changes, this can be different types. It can be electrical, electrochemical, optical, magnetic, thermoelectric, or thermometric, mass electro, etc. and so on. So these are the different receptor property changes that can happen during the process of sensing. So typical response pattern, if you see, is something like this. You have a signal, that means a sensor will give a signal. So there will be baseline initially. And whenever an analyte was introduced into the sensor, then there will be a raise in the signal or drop in the signal. Whatever, there will be change in the signal. And once you cut off the analyte, again it will drop down. So this is a typical behavior for a continuous flow of analyte. That means I am continuously flooding the analyte into the sensor chamber. So these are the different parameters we come across in terminology: response time, how fast the response sensor will respond, and retrace time. Not only the response, but also it has to recover back. So how fast it can retrace back, and dynamic range. So what concentration range it can sense. And finally, the linearity, whether it's a linear behavior or nonlinear behavior in the dynamic range of sensing. Finally, the most important parameter, sensitivity, how fast or how slow. So this is another typical pattern where you will see generally in gas chromatographic type of responses where you will have a pulse injection. So the analyte was, it's like a pulse, analyte pulse was introduced. There will be sudden change in the response signal. And finally, again, once the pulse was, it's again dynamic carrier flow. The carrier will be carrying the flow, that pulse, and the signal drops. They have a different behavior of response. So here the parameters one can consider as response slope, retrace slope, and also integral area under the curve. So these are the different parameters one can extract from the response curve of sensor. So coming to the necessity, I'll brief about different fields. Agriculture, if you see, now the modern agricultural industry, they look for different sensors, which includes from the temperature monitoring, moisture level monitoring, pH sensors, pH of the soil, and also what are the nutrients or the fertilizers that uptake by the plants or fields, and also the pesticide and herbicide distribution in the space region of the agricultural fields, and electrical conductivity of the soil. These are the different things where electrochemical based sensors were developed for this. And also there is, coming to the part of medicine, thanks to Dubai, in continuation with that, you have a sensors in market to, and also in foreign market to some of these. So it's like a sweat, for example, if I go from a breath sensor, as you pointed out, the acetone or toluene, what are the species that are present in the blood, based on that, medical diagnosis can be performed. And also there is a small contactless sensor which can be introduced in the eye lens so that the glucose levels in the eye will be monitored continuously. Similarly, in the saliva, if you want to, somebody wants to monitor the glucose levels, there's a small chip that will be attached to the teeth. So we can monitor, continuous monitoring of glucose levels is possible. Similarly, skin gas sensor, the odorants, what are the gases that are coming out of the skin. Again, they also give a diagnosis tool for the healthiness of our day-to-day activities. These are the different types of, that means I want to say here is, in agricultural field, you have a core application as well as in medicinal field. Not only that, coming to the space, this is a Navy satellite mission by NASA. So in this rocket propulsion part, they have used a sensor, so which actually senses the combustible gases that are coming out during the propulsion. And this is another thing, mass oxygen instrument sensor, where they have a small chip of about 6 sensors in this. So it's an array concept where you will have 6 different chemical species were coated on this, and they developed a sensor of this particular thing to image or to find the Martian samples, Martian soil samples or Martian atmosphere samples. So this is, and coming to military and security, you have a very low vapor explosives. To detect the low vapor explosives, this type of sensor arrays are being developed, which can monitor different explosive species at very low concentrations. So in addition to that, automobiles, fuel production, like hydrogen fuel production or hydrogen storage or hydrogen transport, these are in all these places we find place the use of chemical sensors. So now in nuclear industry, where the nuclear chemical sensors comes into picture. So if you consider fast breeder reactor for the student purpose, it is a schematic of a fast reactor. So where you will have in fast reactor, you use liquid sodium as a coolant. So you have a primary coolant, primary coolant is a liquid sodium, secondary coolant is also liquid sodium, and the tertiary coolant is low pressure steam. So there will be the heat exchange between primary and secondary coolants, secondary and tertiary coolants. So between in this portion of heat exchange, the high temperature sodium will exchange heat with the low pressure steam, and they are separated by with a small thickness of steel tubes. So this is the core shell model. In the shell, the sodium will be flowing. In the core, here the small tubes, the steam will be flowing. So if any material failure happens at long run or any microstructural failure, then high pressure steam enters into the sodium, which leads to the generation of hydrogen and also caustic products. So these caustic products, what happens is an exothermic reaction, of course you all know. So these caustic products, along with the exothermicity, they can attack the adjacent tubes, and the effect is avalanche. So to control it, we have to monitor the hydrogen in cover gas. What is the argon cover gas is nothing but, being sodium as a coolant, the cover of the argon, the cover of the sodium is the argon. So we call it the argon cover gas. That means sodium is covered with argon. So this argon cover gas, we have to monitor the hydrogen levels in argon cover gas. And also there is a need for monitoring hydrogen, oxygen and carbon in liquid sodium to maintain the heat transfer characteristics of sodium. So in other areas also, reprocessing plants and heavy water plants and thermal reactors also, we have different analytes of interest to monitor, like ammonia, nitrogen oxide, formaldehyde, hydrogen, etc. So in the nuclear industry also, we found various application of chemical sensors to have the process continuous, healthy process. So what are the challenges involved? Basically, the challenges, I can categorize them into two categories. One is scientific challenges and technological challenges. So scientific challenges start from synthesis, characterization, improving the sensitivity, improving the selectivity, bringing down the operating temperature, and improving the lower down the response time, and lower down the response time, and data analysis on the sensor array, so on and so forth. These are the scientific challenges that are involved in tuning or in developing a chemical sensor. Coming to the technological part, instrumentation development. So whenever the transduction is happening, if it is not self-transduction, have to provide details for the have to provide instrumentation for the transduction. If it's self-transduction is happening, then you have to provide instrumentation measuring it. So instrumentation, miniaturization, and low power operating, packaging, bulk fabrication, cost effectiveness, and customized designs with respect to the process. These are all the challenges, technological challenges involved in chemical sensor development. So now I will be focusing on scientific challenges and mostly restricting to three parts: synthesis, selectivity, and sensor array data. So, and basically I work on gas sensors. So most of the examples I will be citing from the semiconductor metal oxide gas sensors, which we develop in our lab. So this is a oxygen species from over the surface of semiconductor metal oxide surfaces. Basically, semiconductor metal oxides, they can make conducting at slight elevated temperatures. So between 100 to 200 degrees centigrade, generally the molecular oxide ion is stable, and between 100 to 200, O minus is dominant, and above 400 degrees centigrade, O2 minus ions are dominant. These things were in situ determinations were made by Burson et al. In 2001. So the mechanism of sensing of metal oxides gas sensing is something like this. So in case of an N-type semiconducting metal oxide, once the oxygen is absorbing on the surface, it creates an electron depletion region. In terms of band theory, the electron is captured from the conduction band, thereby decreasing the charge carrier concentration in the conduction band, which raises the, which will have higher resistance initially. So once we introduce a analyte material like a reducing gas, then again the electron will be given back, which will makes the resistance of the material to come down. So this is a simple mechanism of N-type oxide. Whereas for P-type oxide, it is other way. It produces the oxygen absorption will result in hole accumulation layer, which is nothing but the hole in the majority charge carriers. There will be increase in hole concentration. Thereby, there will be a decrease in resistance initially in presence of oxygen. And once you generate a reducing gas, there will be increase in resistance. So what I have done is, last few years back, we have started a delphosite-based compounds for gas sensing studies. So delphosite basically it is having a formula of AbO2 with copper, silver, with the monovalent ions in the A position and trivalent in the B position. So the first delphosite was reported in 1873 by Friedel, and the crystal state of this compound is reported with Karst in 1946. It is a hexagonal or rhombohedral structure. So it is the AgNO2. This is what I have studied. So if you see the literature, the earlier people tried to prepare this compound from 1964 onwards. In 1964, it's a Croft et al. They have tried. They have utilized high pressure and temperature process. And Shannon et al. In 1971, they also utilized a similar way. And 2002, Clayton et al. They tried ion exchange process. And Kohler and Shahiyari and Dong and Zwiller in 2019. All these people have tried hydrothermal synthesis, which is very facile synthesis. So, but what is the problem in these things? In all these processes, in all these trials, they ended always with either metallic silver or indium oxide or indium hydroxide as their impurities. So they have not prepared a pure phase AgNO2 in all these trials. So the crucial step, what I thought was, it is decomposition of silver oxide forming silver. Because silver oxide is above 150 degrees itself, it decomposes. So this is a crucial step. It was people, I don't know, I don't say they missed it, but they could not achieve it. So then we have a closer look about this study. So Shannon et al., they have directly used silver oxide and indium oxide in water and heated to 500 degrees centigrade at 3000 bar pressure. And solubility of silver oxide and indium oxide is very low, of course, you know. And Shaheriari in 2003, they, instead of water, they use a basic solution, sodium hydroxide solution they have used. And also they use to 210 degrees centigrade and 10 bar hydrothermal measure, so to get the product. So whereas silver decomposes at 150 above itself. So it will require elevated temperature and it requires high pressure also for reoxidation. So the modifications applied to the hydrothermal route. So what we have done was, we also adopted hydrothermal route in preparing, but we have done a small, a different way of approach. So what we thought was the silver hydroxide and indium hydroxide has to stabilize. So our initial precursors should not be oxides, it should be nitrate precursors if I take and hydrolyze them. I can have hydroxide precursors. That's the first change we thought. And also you want to use a strong base, so KOH have adopted. And also to augment the stability of silver hydroxide at processing temperatures, you have to high pressure, so hydrothermal pressures are required. So these are the three experimental conditions we kept in mind and we start proceeded. So for this also further we have approached a factorial design approach where it is like not a single parameter. So if you want to play, you want to make a doll to play, you have to make the equiproportionally have to tangle all the rods or all the all the bamboos. So then only the doll can play nicely. Otherwise, it can't play, it can't dance. So in the similar way, in the synthesis also, the different parameters, experimental parameters, you have to consider to make a best out of it. So we call the factors, which are the controllable parameters, which is in our hands, like X variables. And levels, you say how many levels you can vary at low what concentration to high concentration, low temperature to high temperature. So different levels one can vary, and how they interact. It is not a single parameter, but the multiple parameter interactions, how they are going to help in designing a pure compound. So for this, we have taken this help from the statistics. So that is experimental factor design. That number of experiments one has to perform is L power F, level raised to the power of factors. So in our process, presently we have temperature, hydrothermal route. So temperature is one parameter, and concentration of the base, KOH, and dwell time. How much time I have to keep in the hydrothermal vessel at a given temperature. So these are three parameters I have considered, and we have varied the experimental values in the different levels. One is 3 levels of temperature, 2 levels of concentration of base, and 2 levels of dwell time. So for this, we have to code the values. These are the coding values, and these are the different. They have to perform. One has to perform 12 experiments in this, and so these are the 12 experiments you have performed based on designing a design matrix. So, but considering the intercept term and also the cross terms, you have to design a matrix with respect to you have performed a 2-level block diagonalization. So that corresponds to this, and this is a design matrix for the second block. So what the thing is, you have to need a response. What is the, see, I need X variables. These are X variables, my parameters. So what's the Y variable? What is my output? My output is the phase purity. So the phase purity adopted from the intensity of AgI and O2, major peak intensity with respect to the all the total impurity, major peak intensities of the impurities if at all they are present. So considering this as a response, we performed this factorial design approach, design matrix. So with respect to that, so we calculated the coefficients of this matrix, coefficients of this response matrix. So these are the final results. So what we found was the temperature is having a positive effect. That if I increase the temperature, my response will be fine. That means I will get a better pure product. But in the block 2 experiments, that means block 1 is 150 to 180. Block 2 is 180 to 210. If I go from 180 to 210, it has a negative effect. That means the synthesis will go bad. I will not get my pure product. So it tells me that I can use 180 as my output temperature. On the other side, not only individual effects, but the dual effects, binary effects, if you see, again, binary effect is a negative effect with respect to B, that is concentration of KOH. That the higher the concentration of KH, even the higher the temperature, it is not going to help me. So that's what it is telling to me. So finally, I have arrived something like this. Among this particular thing, this is a particular thing. That means I have to use higher temperature, 180 degrees temperature, and lower KOH, 4 molar KOH as my experimental parameters to get phase pure product. So this combined effect of 180 degrees and 4 molar KOH are the more suitable conditions for the formation of pure AgNO2. So this was the work carried out by one of our students in our lab, Beatrice Vina. So for this one challenge, that means what I told is this, getting a suitable compound of interest is one of the challenge in chemical sensors. The second thing is selectivity. So it is an expression of whether a sensor responds selectively to a group of analytes or specifically to a one particular analyte. So for example, if I see, as Professor Dubey also shared some information, so this is what you call it as a cross selectivity. That means the particular sensor responds to different analytes. It's not a single analyte. So similarly, AgNO2 composite, that means whatever the phase, different phases, whatever silver and indium oxide phases, those things, it has a cross selectivity. It responds to hydrogen as well as it responds to nitrogen oxide also, 50%, at 50% sensitivity. So this is having a cross selectivity. So how we can improve selectivity? The phase pure AgNO2, whatever we have done, that selectivity was improved. It has a very little sensitivity to LPG, whereas it's a major size. And also selectivity was improved also for AgNO2 towards hydrogen. But other things are all almost at the baseline. So without expecting, without having, because the earlier impure phases of indium oxide, even it can be very low level of detection of XRD also. They can be, they will lead to cross selectivity and they will lessen our sensitivity. So, and also whether you can utilize this cross selectivity for multiple analyte sensing. Yes, by considering response and retrace kinetics. Even the sensors are cross selective, but the way the kinetics of their interaction can be different with respect to analytes. So one can utilize this retrace and response kinetics to differentiate different analytes that can be present. So finally, the sensor array data analysis. This is all fine with one sensor, single sensor, but they have multiple analytes and multiple sensors. Then obviously you have to handle a huge amount of data. I'm talking one sensor, maybe 10 responses is fine, but I have 10 sensors and 10 responses. It will be very difficult. So how to handle that? For that, you have very hidden features. What are the features I showed in my earlier slide? Retrace time, response time, sensitivity, all these things. All these things can be utilized in the, what you call analysis of this data. So with the help of BIT students, because they have practice school students come for the project. So this is during COVID time, they have done a remote project. That time we have offered this project to them. So along with them, I worked developing a Python program application for analysis of the data. So multiple sensor data with multiple signals. Once you plug into this particular program, what this toolbox will give me, the data matrices generated with all the different features, whatever I have quoted. And those things you can utilize for multivariate analysis, for principal component analysis, as Dubey mentioned, in addition to that hierarchical clustering, k nearest neighbors, all these things can be adopted to understand and to resolve different analytes. And also multi-analyte calibration also can be performed with what I call multi-regression tools. So that for that, this data matrices generation, we made it very successfully. So conclude, application process specific sensor and sensor array development. So these sensors are not like a universally you can use any sensor for anything. It's a application oriented. So depending upon the customization is also very required. Is it a process stream or is it a standalone stream? And similarly, real field application of sensors is also very important. And utilization of machine learning tools in either screening of materials or in correlating intrinsic properties of materials with response characteristics. This is one thing we are trying to correlate the sensor response characteristics with this intrinsic properties like electronegativity or ionization energy or electronic configuration of the materials, where we can correlate any, we can bring out any understanding between them. So these are the sensors developed in MCMFG in our group. This is SNO2 is a basic sensor for hydrogen in argon cover gas. So it was the thrust response in a engineering scale facility. Engineering scale facility, I mean it is argon cover gas about 1 ton of sodium, liquid sodium. And this is the another from a section from our division. They developed electrochemical hydrogen meter for determining hydrogen in sodium. And I belong to, as I told you, I belong to novel chemical sensors section, and it is headed by Dr. K. Gnanashekar sir. And these are all colleagues, Dr. E. Prabhu, Krinsha, Abhijit, Lakshmikant, and Ravindra Rao. There are day to day we'll be working on it. And these are two students, Beatrice Veena and another student working now in our lab, Lisa John. And very much thankful to project students from MSc, MTech as well as BITS Practice School, and also colleagues from our chemical facilities and engineering division, Jay Prabhakar Rao, Premnath and Gunashekaran. They provide the electronics and instrumentation support for us. And also glass flowing and workshop people, they do wonders because we will be having the ideas, but to put them into the experimental design, they have to design and give us. They have to fabricate and give us the equipment. So they help in us way. And also, I also thankful to our head of the division, Rajat Ganeshan, and Associate Director Jayaraman, and Director Dr. Shivaramasu. And finally, thank you. And I will end up with this one, Sahana Bhavatu, Sahano Bunatu, Sahaviryam Karavabahe, Tejasvina Vadhitamastu, Mavidyushamahe. Thank you.
Thank you, Dr. Sriramurthy. Now the session is open for discussion. Yes, Chetan.
Hello. Yeah, good afternoon, sir.
Yeah.
Sir, very nice presentation. I liked it. I actually have a very simple question. In case of like customizable sensors where you use like where you're sensing multiple analytes, like since you're using the same metal oxide, like I assume with my limited knowledge that the number of signals that you get, I mean, it's within a limited spectrum only. So what is the maximum number of analytes have you actually sensed, like through
Actually,
using one metal oxide?
Actually, one metal oxide, see, it can have cross selectivity to multiple analytes.
Yeah.
So it is not there in our hand. It depends upon the nature of the metal oxide. But you can tune the temperature of operation of the same metal oxide, maybe from 200, 250, 300. Maybe the interaction of A with at 200 will be different. Interaction of B at 300 may be better. So you can tap the potential of the operating temperature in case of a single metal oxide to have this interaction between, I mean, kinetics of interaction between the metal oxide and the analyte species, so that depending upon that, you can choose the temperature of operation even in the case of single metal oxide.
Okay, sir. One more thing, like, have we actually tried developing any customizable sensors for like NIN sensing and all?
Now we have basically gas sensor for new reactor applications you are doing. What sensing?
For NIN sensing.
Anion.
Yeah, NINs.
Anionic sensor. This whatever the ECHM I told, it's basically similar to anionic sensor. It's an aqueous solution. Our lab we have not. But there are few people. We have one of our colleague is working on cationic sensor, tetravalent cationic sensors in liquid solutions, but still it is very early stage.
Thank you, sir.
Multivariate analysis, yeah, I'm here.
Yes.
Multivariate analysis, whatever is done.
Yeah.
So that algorithm, it is a completely blind analysis.
No, it's a well established algorithm from statistics.
No, I am not asking that. My question is that if I give some completely unknown sample, your algorithm can extract.
No, we have to. This is what you call supervised learning only. They are not unsupervised learning. Of course, algorithm is unsupervised learning, but I should have a prior calibration of the data from the mixtures. Mixture calibration has to be done.
And
I can say it is different, but I don't know what is what. If I want to map exactly what it is, you should have a calibration.
Okay, and there is a restriction in number
of components. In the sense, components
means how many spectral components are there? For example?
No, actually, the basic idea of this PCA, whatever I adopted so far, and I will testing first, it's a dimensional reduction technique. So you have an n-dimensional data. That n-dimensional data you cannot visualize in n dimensions. So you are redundant, you are brought down them into the lower dimensions, so the 2 dimensions or 3 dimensions. But it's like something geometrically, it's like a projection of n-dimensional data onto a 2-dimensional plane. So that's what we are doing basically, without losing the information in that n dimensions. So that from the scree plot you say, so you can know it will actually, it's a, what do you call, this eigenvalue eigenvector problem. You are calculating the eigenvalues. Basing on the eigenvalue decrease, you can find how many axes are sufficient or how many variables are sufficient to represent the same thing.
Yeah.
That you can plot down. That parametrically you can do that.
Okay, so if there are no more questions, let us thank again Dr. Sriramamurthy. On behalf of the organizing committee, I want to facilitate you with a memento. With this, all the technical sessions are over. I will hand over the mic to Arindam.
Thank you, Yudraj, for chairing this session on behalf of so with this, we come to the end of this sessions. I will go for lunch, but before we go for lunch, I'll to have the photo session just outside. And also with this, my job as a compare of this event also come to the end because the validation function will be taken over by our HOD. So you travel safe back home and hopefully we'll meet again next year. Bye-bye.
Mm-hmm.
किस ओर चली कैसी संग्राम संदन की लहरें आएगी क्या किस ओर चली कैसी संग्राम संगम की लहरें इलाही मेरा जी आए इलाही मेरा जी आए आए थी जो शिकायतों को कुछ तूने कुछ मैंने सुलझा दिया। जिंदगी हाँ थोड़े थोड़े फासले थे, कुछ तेरे कुछ मेरे क्यों दरमियां। जिंदगी हाँ थी जो शिकायतों को कुछ तूने कुछ मैंने सुलझा लिया। तेरे इशारों पे मैं चलता रहा, इशारों पे तू भी चल कभी। तेरे इशारों पे मैं चलता रहा, मेरे इशारों पे तू चल कभी। बह चला मुसाफिर कहाँ बह चला, बह चला मुसाफिर कहाँ बह चला, चला। जिंदगी हाँ टूटे टूटे तुमको को चुनते जिंदगी हाँ छोटे छोटे पर लेकर देखे जाए कौन आसमां। कतरा कतरा मेरा 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 फिर तू भी बिखर गई। कतरा कतरा मैं चुनता रहा, कतरा कतरा तू बिखर गई। बह चला मुसाफिर कहाँ बह चला, बह चला बह चला। चुपके रात तुम आंसू याद है। चुपके चुपके रात तुम आंसू याद है। हमको अब तक आशिकी का जमाना याद है। चुपके चुपके रात आंसू बहाना याद है।
Any portrait.
Hello, mic testing.
Yeah, ah, ah. You have to check that guy. One is hanging. Allada. Duplicate ஆக மாட்டேன் அது நீ செய்யறதுங்க duplicate பண்ண
word here at the predictory function. First, HBNI interaction with the chemical. I request Sir P.R. Vasudev Rao, former Vice Chancellor, HBNI, to come on the dais and chair this webinar. Also, I request other dignitaries, Professor Dilip Kumar Maiti, Associate Dean, HBNI, Professor S. Kanda, Director, Radiochemistry and Isotope Group, Park, Sir C. N. Patra, Senior Scientist, Park and Head of ACD, Sir S. Srinivasan, Dean, Faculty Affairs, NICER, Mansu Biswal, co-convener. First, my apologies. I request Professor Ramananda Rao to on dais, please.
Yes, so good evening to all of you. We have little bit change in the schedule. Before we start the validation, we would like to thank a few of our sponsors here. Like to give I request the convener, Dr. Sanupan Empena, give away the token of appreciation. So let me call who are here. I'd like to call the representative from Interp Instruments to come on the dais. Collect. Thank you. So next one is the representative from Thermo Fisher Scientific Instruments. Can you please come on the stage? Representative from Maya Technology Services. So thank you all for your kind help. So it contributed a lot for us to organize the meeting successfully. Thank you again. I will request Dr. Nampena to continue the presentation.
Hello everyone. Once again, I welcome all the dignitaries on dais. Professor P.R. Vasudev Rao, former Vice Chancellor, HBNI. Professor Dilip Kumar Maiti, Associate Dean, HBNI. Professor S. Kanna, Director, Radiochemistry and Isotope Group, BAR. Professor C.N. Patra, Senior Scientist, BAR and Head of SED. Professor C.V.S. Brahmananda Rao, Head of Solution Chemistry and Mass Spectrometric Studies Section in the Fuel Cell Chemistry Division, IGCAR. Professor A. Srinivasan, Dean Faculty of ACE. Dr. Himanshu S. Biswal, co-convener. And all participants. Good evening, everyone. Last 3 days, we enjoyed all the invited talks, starting from the keynote lecture by Professor Sundar Gopal Ghosh from IIT Madras, and the last speaker of the session by Dr. Sri Ramamurthy from Nitika Kalpaka. More importantly, we all appreciated the 2 poster sessions conducted on day 1 and day 2. As per the program schedule, all oral presentations have been conducted in the last 3 days, and also posters except Mr. V. Sukumaran. Due to some unavoidable circumstances, he could not attend the event. I congratulate all speakers, presenters, chairs, poster jury members, and all participants. All of them did a fantastic job. Please give them a big applause. This kind of subject-wise interaction meeting must be conducted once in a year. I request senior members to consider how we can move forward and guide the young scientists and students. The purpose of the meeting is to establish possible collaborations among faculty and students of DAE units. I believe that we are partly successful in this issue. One can anticipate high-quality publications and patents through collaborative works from HBNI CI, OCC units in the coming years. I enjoyed this meeting. Chemistry is essential for meeting our basic needs of food, clothing, shelter, health, energy, clean air, water, and soil. If you want to address societal problems, all experts in different fields must come together. I feel this kind of meeting is a perfect platform. More importantly, I request that each of us assemble here in this meeting. We have to popularize chemistry at school and college levels, demonstrating some chemistry experiments and giving lectures so that we can attract young and brilliant minds to the chemistry. Our HBNI main office can also think in that direction. In addition, I wish HBNI to obtain a national importance, Institute of National Importance, that is INI. I was told that it is under process. If HBNI is successful in that, all our problems will be solved. With this, I conclude, and once again, I congratulate all of you. Thank you. Now I request Professor S. Kannan, Director, Radiochemistry and Isotope Group BAR, to express his views on this event.
Good evening to all. Respected Professor Vasudev Rao, former Vice Chancellor at HBNI, Professor Maiti, Professor Srinivasan, Professor Biswal, Professor Ranappa, Professor Patra, Professor Brahmananda Rao, and other my colleagues from BARC, IGCA, and ISER, and my dear students from NISER, IGCA, and BARC. Welcome you all for the valedictory function. As you know, this idea was originally started in 2020. It was month of January or February, we have a BOS meeting. So we have planned to have this type of meeting. We want to have it first in chemistry. So BOS also approved, and we approached Vasudharao where to keep it. He suggested to keep in Kalpakam. So we went with that, but unfortunately because of COVID pandemic, we could not go further ahead. So we started after 3 years in 23 in NICER. So that way NICER is creating a history. The first meeting is held in NICER. Otherwise you would have got it in Kalpakam. So this is one thing. And second thing is, the purpose of the meeting is to share the knowledge, at the same time, they share the facilities within the CIs. Because some of the institute, they have many more instruments, whereas some other institute, they may not be having. So I feel that student level interaction is much, much better than the approach from the top. Like when you go to nanomaterial synthesis, people are telling top to bottom or bottom to top. But always you can see most of the people synthesize from the bottom to top, nanomaterial. So it is very difficult to break from crystal to a nanomaterial. So here also, the bottom line approach is much, much easier compared to suppose I am writing letter to Srinivasan writing to his student. Rather, my student and Srinivasan student, they interact, that will be much better. This was the purpose, this was the idea started in 20, and it's the first meeting. So I want that whatever the process Saranappa is telling, yes, we like to have next meeting, either it will be IGCAR or it will be BRC. But you should also remember the facilities which are available in BRC is something different from NICER. Because mostly 90% of the students, I can say, work on radioactive material. So most of the instruments are inside the glow box. Some of the material we handle also, like in the periodic table in the last one, that is 5F element. So the facility is something different. At the same time, you people from NICER have an opportunity to see all the facilities, how the people are working. So this is an introduction, or I can say this is a starting point. And you know, HBNI is, as Saranappa is telling, yes, we are in the process of getting Institute of Excellence. If everything comes, then our HBNI and all the CA Institute of HBNI will be coming in the world map one day. It may be very soon. Another thing is about the NICER. See, this is like the 3 days meeting, really we enjoyed. That is from BARC as well as from the IGCAR. So how you can see that when, I don't know about nowadays marriage, but in olden days, in our time, when a bride is coming to a groom side, so the 3 days they'll treat it like, very important. If something has happened, then they may think that this fellow may not stop the marriage. So not only for the bride, but also all the relatives of bride also. So here for last 3 days, so we are, of course, we are all from same family, but nicer people treated as a bride side. So they are taken care from the airport till lunch, dinner, and tea, snacks, everything. All the people enjoyed. I think I am also feeling that all other my colleagues from IGCAR and BRC also may be feeling the same feeling. So I want, this is the first one, we should continue. I thank to NICER, all the people starting from the Professor Panda to all other colleagues for your excellent hospitality and fruitful interaction. Thank you very much.
Thank you, Professor Kannan, for your views. Now I request Professor Brahmananda Rao, IGCAR, to express his views on this event.
Evening to all, dignitaries on the stage and off the stage. My dear friends, I think, as they say, all good things come to an end at some point of time. And as Dr. Kannan has told, the last three were we enjoyed the place because it's the first visit for me per se. We have not been here. And I think Dr. Sharnappa and Biswal, the way you people organize it, I think you have put it at a higher level. So it becomes a really pressure on other people to be at par when we conduct the program at IGCAR. I think immaculate, everything is perfect, nothing to even question those things. Everything was up to the mark. And I see a lot of people in the back end, a lot of students working hard. I think they are the soldiers of the whole program. A lot of work they have carried out on the back end. And I know that because I have been at the other side many times. So a lot of work goes on the behind to make the things so perfect. And I think I should congratulate all the students who are involved in this program. Without you, I think it's not possible. not only for organizing it, and of course, the poster session, the work part of it. I think this is one of the best ideas because to interact with our own fraternity across IGCAR, BRC, and this is a very good idea. I think we should take it forward. We will do it. And as Dr. Kannan was saying that some of the areas may not match, but surely I think this is a whichever areas where we can cross pollinate, it will be really useful. It will really be useful. In some of the areas we can't work and your expertise is there, particularly in the organic senses there, I think the people are far ahead of all of us. And the facilities, in fact, I should thank Dr. Biswal to see all the facilities. They had a beautiful library, and I think one of the best facilities we have. It's only thing how you, because NICER is somewhat different from other institutes because it's completely more academic oriented. You can do blue sphere research. So I think that facilities we may not have to a certain extent. And I think if we work together, it will be really great. I think we can go together, progress together. And NICER is the only institute which is both academic, where MSc program is there, which we don't have in our institute. So I think the way things are going, it's going to be great in future. So let us, as the whole purpose is to go for what you call coordination, work together. In fact, yesterday with Sharnappa, we discussed a lot of things, and the excitement in main group chemistry, which we never thought was really, I think it was really a enlightenment for us at least. And we have seen other lectures from Nagendra Sharma. I think the work is so beautiful. Absolutely, I don't think we can even imagine that we can do at that level at our place because our mandate is completely different. I think it's a great platform, and I should congratulate all of you for making it part of it, and we hope to see and we'll move together. And I think I should congratulate Arindam Ghosh. I think it was a great VJ, the way he has conducted the whole program. I think he's not around, but I think it's a great job. So I think let us move forward. It's anyway beginning of the whole program. So we have a lot of time. Every year, if we are going to meet now, at least we know each other. Next time we'll be more closer. We can talk better, interact better. And I think we have contacts of each other. Let us move forward. I think it will be a great, we have to elevate the standards of HBN. Already it's at a higher level as Institute of Excellence. If it comes, it will be really great for all of us. So I hope this is a great program and we'll continue to do so. Thank you all for the opportunity given.
Thank you, Professor Brahmananda Rao. Now I request Professor S. Srinivasan to express his views.
Attendees on the dais and off the dais, my dear colleagues and students. Good evening to all. In the first lecture, I prepared so many things. Today, I did not prepare much. However, there are both the points which we have addressed in the first meeting, which is we try to push it as much as possible so that at least we get some response or the answers from the HBNI team. There were one more issues where the ISA Pune student, there are the first year integrated MSc student when they have come for the student admission, then that time they also started telling, sir, ISA Pune is the separate institute where they will be, so they have the better visibility than what we are with the HBNI team. But so we are with the HBNI team, that visibility we are trying to push it as much as possible so that the students will stay back with us, remain, and they need not necessarily to explore the other possibilities or other venues because we have our own examinations so that the students will stay back with us and explore the other venues. There are the interaction part which last 3 days which we have tried with so many other things. And particularly this instrumentation part is a very important thing where the HBNI, where the PAC is asking the questions again and again. Whenever we have sent the proposal back to FIFTIS, the budget proposal is more than 1 crore. Obviously, it will go to, it is a single tender, it will go to. Then BAE will clarify the things available in PRC or available in IGCAR, all those such issues are coming up. So before going to such a thing, we have to make sure that right now we have the interaction with all both the IGCAR team as well as the BRC team. But we will have the better understanding before taking such an issue to go to the EOG or the PSC or the PAE so that that issues or the duplication of instruments can be avoided. So that is one such issues which we have to take it a bit more carefully so that
the problem will be sorted out at the initial stage itself. Thank you very much. So our colleagues have put so much effort, and also the student volunteers have put tirelessly, along with our convener and co-convener of this meeting. We have all, everyone have done the good work. Hope there are no shortcomings which I have also mentioned. If there are any shortcomings, which I have not received any complaint, maybe they might have conducted the convener of the program or the co-convener of the interaction meeting. So far, I have not received anything from them. So hopefully you have enjoyed the stay, and I will also have a final say that have a wonderful return journey back home with the sweet memories from myself. Thank you very much.
Thank you, Professor S. Srinivasan. Now I request Professor Dilip Kumar Murthy, Associate in HBNI, express his views about this.
Good evening. Professor Basudev Rao. Yes. And faculty friends, other friends of the dais, and of course my dear student friends. So last 3 days, I hope all of you have enjoyed all the talks and even poster session by all the students. And of course, the food, your stay, everything is taken care very nicely by NICER. I think Professor Saranappani, a big round of applause. So the whole purpose of this meeting was to initiate interaction among students and faculty members of different CIs. I think it has been seeded, not only seeded, I guess few collaboration will start from tomorrow onwards. Already in the meeting also people are saying that kind of collaboration will start. Here I add that though it is only for within the HBNI family, after my talk, Professor Ghosh, our keynote speaker, he told me that I want to collaborate with you. So that's at an extra thing I got from our keynote speaker. So I hope the same way there will be a lot of collaborations. And now probably nicer faculty members and students know at least a fair glimpses what are the facilities available in IGCAR and BRC, what kind of work they have been doing. In fact, Professor Malya, he gave a beautiful presentation and he invited that you have the strength in synthesis. So probably you can start collaborating to get a end product, go to the final, to the societal benefit. So that kind of collaboration, if it comes, that will be the real success of this meeting. And we have planned that we had a meeting in last April about all discipline and all CI that was in Mumbai, and that was a great success. Now we are moving to individual discipline, and already life science meeting in Indore was taken place in September, and they have initiated few collaborations like life science, physics people, they have come closer, life science and Tata Memorial Center and Tata Memorial Health Center, means hospital, cancer research, they have come closer to start some collaborative work. So here also, at least within chemistry, we hope that few collaborations will initiate. And if you need any help from central office, we are always there to help you. And this meeting, we plan that all discipline and all faculty members kind of meeting, that will be in alternate year, so that some cross-discipline collaboration may initiate. That's the whole purpose. And here, it is within the discipline, maybe application in different area we have initiated. And all these, whatever I told, this kind of interaction, we have another part of interactions also. We thought of many people are working in silo. Let's come together and work on a big problem. So, and not only that, to know each other, even our students, those who are in NICER, PhD students, probably some of them have gone out with PhD degree, but they have never seen a nuclear reactor. We have research reactor at Mumbai. If some of the students are interested, HBNI give travel support for that. In fact, that program is there. I think before lockdown, some people from physics department from NICER, they visited PARC, different facilities. I think right now it is going from DCC, some about 20 people have gone, PhD students. They have gone to BARC and physics people, and they are visiting BARC, including research reactor Dhruva or other facilities, accelerators and all. So such opportunities do exist, including for the faculty and as well as PhD students. And for the PhD students, HBNI has some provision for travel support. That kind of option is also there. And let me tell you, all these initiative was taken by none other than Professor Vasdev Rao. He initiated it, is his idea with whom we are taking forward. That's the whole thing. We are taking forward. And well, some problems, people are saying that, well, there are different kind of problems how to solve. Probably when we become INI, everything will be solved. Yes, HBNI is trying hard. The department is very much interested to make HBNI as INI so that we come out of UGC rules. UGC has many rules. Means one can say that, education is kind of over-regulated. UGC has made it like that. If we become INI, probably it will, lot of freedom will get it, but nothing comes free. If we are INI, we have to be more responsible so that the standard and other part, we keep it. So responsibility will be, on the other hand, will be that, all faculty members as well as for the students, that to keep the standard or even move away. So to take to higher and higher steps. So that will be one point. As soon as it's done, we'll be very happy. But I don't know what is the government's thinking. It is pending for quite some time. But we are following regularly through department. And I think that's all. But regarding kind of another problem, you are talking about that some students have problem publishing 3 papers, which is the Board of Studies requirement. It is not like that. The requirement is the doctoral committee should be satisfied that whatever the work is done by quantity and quality wise, it is enough to award PhD degree. That's the basic requirement. But the guideline HBNI has given for chemistry, it is 3. It is not just HBNI, because Board of Studies members, Board of Studies is comprised of members from all the institutes. So whatever they have recommended, based on that only it has come. But at the same time, if doctoral committee feels that somebody has developed an instrument and maybe just one paper he has published, that should be enough to award a PhD degree. So, or somebody has published only one paper, which is equivalent to some 10 papers, maybe he has put almost 5 years effort to just synthesize some 100 steps reaction to one product, which is, just to can be published any high impact, the best journal available. So in that kind of case, one paper is enough. But there is a guideline from UGC that at least one paper in peer-reviewed journal has to be published. So that's why we are talking that minimum 1. But other part, if enough work is done with quality and quantity, there will be no problem to get PhD degree. It is a wrong notion. Somehow it has come that this is must. It is not that. We have given guidelines, but quality and quantity both, of course, BOS will very carefully observe, and that's why they say, sometimes they say, no, you need to publish more paper. It has come back. Many times it has come back. And one has to follow that, because they are the subject specific experts. Whatever they say, we have to, honor that, because they are not arbitrarily saying someone or putting load on someone. So with this, I stop here, and thank you all. Thank you, the team, Professor Saranappa and from NISHR and other, and especially student volunteers. They were running here and there, I have seen, and very nicely they are coordinating with all the events, everything. So thank you all for everything.
Thank you, Professor Dilip Maiti, for your. Now I request Professor C.N. Patra, Senior Scientist Part and Head of ACT, express your views, and also I request you have to do another job. You have to announce. You are the one of the chairmen of poster sessions, and I request you to announce best poster awards.
Professor Vasudev Rao, former PC and former director in the Center for Academic Research. Sir Kannan, Chairman Board of Studies. Sir Srinivasan, Head of the Department of Chemical Sciences, NISER. Professor P. Associate in HBNI. Professor Brahmananda Rao, in Academic Technical Sciences of HBNI. Professor Saranappa, and Professor Himangsu, who are the conveners and co-conveners. So Kannan as well as Professor Maiti has told what was the, what was the strategy behind the interaction meeting, and I think every one of you will accept that it has succeeded. In fact, 100% I should tell. It's not only the collaboration, it also gave a glimpse of many facilities which are available not only in NISER, also in all the CIs. In fact, let me also tell you, being head SAD, I am inviting all of you, whoever feels anytime it is necessary to use SAD facilities, please approach me personally. I will be extremely happy to open the facility to you. Please. Now, I will also have another request. Of course, now I am part of HBNI, so I also have another request to HBNI that, like national academies, they invite the undergraduate students for carrying out research for a few months. HBNI also can initiate such a thing, that they can recruit certain undergraduates and give it to CIs. Because what will happen, then they will, we will basically throw the seed in them, how to carry out the research. Because all the facilities are at our disposal. But you know that in most of the institutes, except of course NISER, maybe CBS, we are not getting regular students or good students ultimately. So this is one of the idea I should tell that HBNI should venture into, in case we are able to do it. So catch them young. In undergraduate itself, if you can catch them for carrying out, let us say 3 months, 6 months, whatever it is possible for their degrees, then it will be very helpful for all of us, catching them young, so that in my next step, it is in most of the cases they will come to us. Coming back to this the course also, I saw that HBNI has started research methodology. I should request not only chemical sciences, for all subjects, in fact, they will start learning this. Because it is not only working, hard working that matters, also writing papers. And I am sure everyone will agree that the first paper is not written by the student, it is written by the faculties. I can 100% assure you, it is written by the faculties. Because, see, the writing of the paper itself shows that it is written by the voice. But we have not seen this. We never see it. So research methodology is one of the courses I will tell that everyone should go through. I am sure NISER also might have a course like that. And coming back to this meeting, see, it is not only that they have succeeded in, for collaboration. I'll also hear the team, Saranappa, Himangsu, Srinivasan, as well as Arindam, for giving exceptionally good logistics, hospitality, and food. I think they deserve another round of applause. So we thank them profusely. And let me tell you, there is no shortcomings. We are extremely happy. Being in BRC also, we are extremely happy. And we really feel after 3 days of so much of deliberations that our knowledge is good. And we'll be extremely happy if the students also feel so. So it is not necessary that we should only feel. So I think I will stop here and then I will declare the poster results. So let me first of all tell you that all posters were equally good. All posters were equally good and it was extremely tough for the judges to decide which one will be the best. But judges have a work to do. They had to do it. That is the reason we have to choose some and we have to remove some. So please, we sincerely apologize, including all the team members. I will tell Dr. Hassan and all these people that please, we sincerely apologize that if somebody is not getting it, do not think that his or her poster was inferior. Let me clearly clarify this. But we have to judge it, that's why we will judge it. So I will tell the 6 names. Yeah. I will request Professor Rao to hand over the prizes. Sir. So these are not in any order. The names are not in any order. We have 6 prizes. So the first one goes to Omit K. Sharma, BRC, PP05. PP05. So no first or second, it is not in order. 6 prizes will be given. The second name which comes to Saurabh Mandal of SINP, PP11. The third name which comes to Rajat Kumar Sahu, Nizer, PP18. Fourth name which comes to Sudhika Manna, BRC, PP27. Fifth name which comes to SB Subramaniam, Nizer, PP34. Last on the sixth name, Dada Surya Prasad Ajikar. Please. Hearty congratulations to all the winners, and now I'll hand over the mic to
Thank you, Professor Pavda. So, all poster award winners will get cash prize 2,500 from the HBNI. Okay, please, once the function gets over, please come here and sign one document. Okay, thank you. So now I request anyone from the audience who wishes to express your views about the event, faculty delegates, and also followed by students. Importantly, outside delegates, anyone wishes to express your views about the event, please come. Professor Malia, can you come and express it?
Very good evening to all of you and all the dignitaries on the dais. Well, it was a wonderful experience for me to be here. And even before my presentation, I had the opportunity to talk to many of the students who are doing wonderful work, especially in battery technology and all. Really impressed. But more importantly, well, I don't know. Anyway, the meeting was very good. But I have one request to NISA. In fact, we discussed this yesterday with Srinivasan here also. Since all the people are here, see, the problem is, even we face, and I am sure that many of the students will also be facing the same problem. Our work is not going with full swing just because we have a lot of problem with the characterization of compounds. So even the students may be facing exactly the same problem. In fact, when we came here, we brought a lot of mass samples to get it done from NISA. So is it possible that those who are here, they can take up this forward, and why not have a centralized facility for all of us, rather than all the institutions are having their own things, or else there should be a provision that there can be samples taken from the other HBNI institutions and channelize it so that the work is not hampered. Anyway, we are very much interested to collaborate with all the ICERs or ICERs, whatever. In this way, we can decentralize our work and do more and more productive work, which will be useful both in society. So that is my request. And rest of the things, I feel the hospitality-wise, stay, food, everything was fantastic. And I like this, take this opportunity to thank all the students here and all the people behind this conceiving as well as executing this wonderful meeting. Thank you so much.
Thank you, Professor.
Anybody else from student side or from IZCAR scientists? Any? Please.
Good evening, one and all. I'm extremely delighted to be part of this first HBNI meeting organized by NICER. And certainly, as people pointed out, that exchange of ideas have happened, and definitely there will be more collaborations which will happen in the near future. And we are also looking forward to that kind of things, and especially Madhav Malaya is very much interested with respect to uh, the design of ligands or something. And like it, even though he's my batchmate, and all these ideas have happened only in this platform. I'm extremely happy for that, and definitely in future many collaborations will happen. And with respect to the organization of meeting of this kind, special thanks to Professor Sharanappa Nambanna. And normally, organizing committee, once the meeting is organized, they will not bother about the preference of individual or something. But it is amazing that Dr. Sharanappa is asking, is focusing on everybody, and he's inquiring about all the arrangements, whatever have been made. I think we should give a big round of applause again for Dr. Sharanappa. This is the first time I'm seeing a person of this kind who take care of all people actually. And with respect to students, and this meeting is organized for students. And definitely, I want to congratulate all the students and for doing a wonderful research. And your effort is sure to win. Keep up the good spirit. All the very best to all of you for a fantastic future ahead. Thank one and all. Thank you very much.
Thank you, Professor. Anyone from the student side? Outstation students? BARC, IZCAR, or SNP Kolkata students? Please.
First of all, thank you for giving me the opportunity to share my views. We are extremely happy with the hospitality we have got right from picking up from our respective stations or airport and guiding us to our accommodation, however early in the morning or however late in the night. The volunteers and the team have done a very good job on that. And I'm sure that all of us are feeling that we are at this point we have a little bit more knowledge because of these discussions and these talks, and will be extremely happy if our goal of collaborating and doing science together goes more forward and it happens more firmly. And at the end, thank you everyone and all for all the things, for the nice experience we have in Bhubaneswar. Thank you.
Thank you. Now I request, it is a great honor for us, Professor P.R. Vasudev Rao, former Vice Chancellor, HBNI, is here with us since from last 3 days. He attended all talks and he even visited our department, and also he has gone through all the posters. Now I request
chairman of this event to address the gathering. Fellow members of the chemistry community and budding members, students, very good evening. I begin by joining all of you in conveying my great appreciation to the nicer team led by Professor Sharanappa for the excellent organization of this event. You have set some benchmark now. Now, next meetings, they will have to look at it and ensure that the same standards are kept or standards are further improved. I also want to congratulate the winners of the Best Poster Awards. As was mentioned by Professor Patra, it is not that the other posters were any less in quality. I personally just spent a few seconds or less than a minute in all the posters. I went around and I could see very animated discussions also between the students and many of the members, other faculty, etc., which is a very good sign for the science. And I congratulate all of you for putting in the effort. Coming back to the event itself, we know that only part of the work carried out in each CI has been presented. If you take BRC or IGCAR or NICER, only some portion has been presented because what could be done in 3 days is limited. We had a number of, even though we had to limit each talk to half an hour so that we can accommodate more people. Even then, some people would have liked to speak for 45 minutes actually. One could see that there is enough material. But to accommodate more people, we had to do it for half an hour. Even then, it's very clear. So therefore, it's a good idea to repeat it every year or a little, maybe every alternate year at least, at different locations and give opportunities for others also to come forward and explain their work. This is one part. Then second is is my suggestion for the HBNI to consider that in the future events, maybe we should have one session of oral presentations also with students, because they can get some opportunity to come to the stage. At least they know they are speaking in front of their own family. It will be easy for them to practice. So we can introduce this in the coming programs, because we have received a large number of contributions from students. So it's not a problem to choose some maybe 4 or 5 or 6 of them to come and present it orally. This is one possibility. The other possibility which I have been suggesting to HBNI is also that if this program grows properly and gets stabilized, it should be possible even to consider participation and presentation in this meeting as equivalent to a national conference participation for the purpose of the PhD degree program. Because as you know, UGC requirement is there that every student has to present 2 national conference papers and 1 paper in international conference. So traveling is not so easy nowadays. And I would personally think, I don't know if you agree or not, I think that presenting in this kind of forum is likely to get much better inputs than going to a national forum where you don't know everybody. Here there are much more opportunities to discuss and much more opportunities for you to grow by talking to other people. So HBNA can consider through BOS whether we can recognize this participation as equivalent to participation in national conference for the purpose of the PhD degree, which will be very helpful also for the students. And second is that I was, of course, listening to all the lectures all the 3 days. I must say that, first of all, I have not been very active in research in the last few years, but I have had the privilege of going through very large number of theses. In 5 years, maybe I would have seen about 1,000 theses every year, 200,000 theses I would have gone through. I am quite convinced about the excellence that prevails in every one of the institutions under HBNI. Each one of the theses really was inviting. I have seen, because I'm seeing the comment from the foreign reviewers and comments from Indian reviewers also for the thesis. Uniformly, they attract excellent comments Of course, there are always a few which require some improvement. But it's obvious, even through the presentations made today, the kind of work which is being done is a state of the art, as far as the world scenario is concerned. Definitely. And the second point connected with that is that I'm equally convinced and more convinced after this meeting that we have even greater potential to rise if there is collaboration between the institutions. I will come to this point a little later. Because we know very well that we also know very well, for example, in this meeting, all the CIs have not participated. Only a few CIs where the chemistry programs are active have participated. But I could see in the presentations that there is a lot of interface with other disciplines as well, including physics and biology. And maybe in the future, sometime, HBNI has to envisage an interdisciplinary meeting also, so that a person working on, for example, targeted drug delivery, it is better that we have in the audience somebody from the medical and or biology community also knowledgeable about this, so that the discussions lead to much better work in future. So I'm sure that this meeting and this concept of collaboration between the CIs has a great potential for the faculty. I will give just a few examples which I noticed personally in this meeting. There are many, many more. Only, for example, the number of presentations from dealt with one presentation from NICER dealt with drug discovery for cancer treatment. But we know that Tata Memorial Center and particularly the ACTREC at Mumbai, which is also a constituent institution of HBNI, is deeply engaged with clinical research and cancer research. So there is a great potential for the work which is being done here getting translated into actual societal application if we have a joint discussion along with TMC. So maybe what could be done is I would request Professor Maiti, after he goes back along with Professor Nayak, he could sit down and work out. Maybe there should be a brief satellite meetings in the next few months based on individual papers which can go forward by discussion. I don't remember the name. I was mentioning to one of the faculty also that he should go to Bombay now and make the same presentation to the colleagues from TMC and BRC, so that the work can be taken forward through collaborations. Other examples of such possibility of collaborations include synthesis of ligands. There were presentations from BRC on radiopharmaceuticals, and there were presentations from NICER also on organic synthesis. So one is very, very clear that there is a great expertise in synthetic organic chemistry in different groups. And these people joined together, it can be really put to use in devising new molecules that can be really high breakthrough value and high societal benefit. There was also discussion about basic research on very, very important topics which can have a lot of applications in not only other industries but also in nuclear industry, like room temperature ionic liquids and deep eutectic solvents. A lot of work is going on at different places, but we also know that there are a lot of applications ahead. So the basic research capabilities of different groups and the application possibilities in the department can be both synergized through this kind of meetings. So that if you come to know what a person can do, it can be utilized, and then later on you can take the application forward. So I'm sure that this meeting will lead to such collaborations which will help improve the excellence with regard to basic research in all the units, and also take many of these activities to logical conclusion for either societal or even departmental applications. I can tell you that I don't want to use this to discuss too many technical things, but I can give you another very good example where there are a large number of very interesting scientific challenges waiting in the department for solution through basic research or much fresh thinking, for example. And one typical example I would say is that uranium extraction from seawater. So this is a very interesting topic because the total amount of uranium in seawater in the world is far, far ahead by several orders of magnitude compared to uranium available on the earth. But very, very difficult to do that extraction because we require ligands which are too specific and they will work in particular conditions. And no, there are many other issues there. Anyway, I don't want to go into that, but these are awaiting breakthroughs. And it's possible that some fresh thinking coming from some basic research group will definitely take these kind of things forward. For this, what may be required, maybe in another occasion, there should be probably 1 or 2 presentations on what kind of grand challenges the department is facing, which can be solved through research. So this should be done both for chemistry. After all, people at NICER or people at SINP, etc., they should be aware about what chemistry problems are very, very important for the department where some work is, we will be happy if somebody works. It's quite possible there is a matching of interest. Somebody says, no, I know already something I've done about this earlier. So it can happen. So maybe we should include 1 or 2 talks in the next program about the chemistry challenges for the future. It can be for nuclear industry or any other industry, but at least the seeding of ideas into people's minds. This is another possibility. Now, this kind of, there was a lot of mention about sharing of literature, sharing of infrastructure. I believe it's an extremely important topic for various reasons. And one reason, now that I'm a retired person, I can always speak up anything. What I can see coming is greater and greater emphasis on use of funding and avoiding duplication. This is going to happen sometime or the other because there is a pressure on funds. So it, as somebody mentioned, it's a very good idea to look at how we can build centers of excellence with state-of-the-art sophisticated instrumentation which can be made available across all the units. This is certainly possible, and I'm sure the department would welcome it because instead of sanctioning one instrument for each center, if they are able to, what I can envisage is that NICER could be a hub for particular activity, and VECC or SINP can be hub for another activity. So somebody will have probably metallurgy, for example. Somebody can buy the latest, transmission electron microscope costing some 40-50 crores, and that can be made available to everybody. So in different domains, different units of HBNI can become the focal point for investment. So this, I'm sure this model is going to happen maybe some 5 years or 10 years from now, but it's better to start in some way. And the other important thing I can understand, maybe Kannan can correct me if I'm wrong. Many important chemistry journals, including Angavante Chemie, etc., very old issues, many issues may be available in BRC, not available in NICER, and vice versa. Even this, if you establish contacts like this, it should be possible for people who seek literature which is not available in their library. They'll be able to write to their counterpart in BRC and get it through BRC library. So this is a simplest way of infrastructure sharing, but very, very effective. So this is also possible. So we need to definitely look at sharing of the infrastructure. And I would think that bodies like the Board of Studies, they should be able to debate on this also sometime, how to give ideas to different people about sharing of infrastructure. Now, these are all about, what I spoke is about generally about research and faculty, but I want to speak something about benefits that can happen for students also, and which we need to think. One is, for example, I have been advocating that in BRC or IGCAR or SINP or any unit for that matter, then ACTREC, excellent courses are available on variety of subjects. All of them may not be available at other CIs. I can give an example that somebody from NICER who is studying for his PhD wants to just learn a little bit about actinide chemistry, and he wants to attend one course on actinide chemistry. And similarly, it can happen that somebody from BRC wants to attend the course being done at NICER on synthetic organic chemistry, which is not available in BRC. It is possible. So if the student, see, after all, the university is being run for students, and the student should definitely have the opportunity to have 1 or 2 electives, which not only are taken in their own institution, but across the institutions in HBNI, which should be definitely possible. And what I have done, at least before I left HBNI, I have mentioned in the academic council also that my suggestion was that the BOS should consider it probably, that let us agree, if we agree, that every CI will offer every year one course on hybrid mode, on which other students can also register. This is not a big deal at all. During the pandemic, we have run courses online all the time. So instead of many courses, suppose in BOS there is a discussion. This year, NICER will offer one course which will be available. So timings can be adjusted so that now everybody can participate. So it can be open to other people. Similarly, BRC can offer one course which will be available to IGCAR or NICER, anybody who registers. So this way, students can have the opportunity to attend, at least have one more course in their kitty, which they would have otherwise not been able to get. This can be another beginning for students to expand their knowledge. So my suggestion would be that the VOS should have a discussion on this in the coming meeting. And one important thing which can be done, because we are now in January, I think it is a very good time for the coming academic year. Is it possible to begin with by making a course calendar for all the CIs and put them together, that students from every CI know what courses are running in other places. And secondly, you can also discuss what course can be offered online or on hybrid mode. No student has to travel. It will be offered in your own institution. Like today's program, you are offering on YouTube. It is possible to offer that particular course alone on YouTube or WebEx for the benefit of other students. So I request BOS to consider it because it will be of great value to the students. Another important idea which was raised by a student in the last meeting which was held at RRCAT on life sciences. I think it was a NICER student only. NICER, the person got up and said that why not organize PhD YOOC on hybrid mode? It's a very important suggestion according to me, because today, even though we call it as a public YOOC, a PhD student presenting the final work in the YOOC examination, she or he is presenting to the same institution, but it's not being heard by other students across. Suppose some student from here is attending a YOOC being held at Mumbai or at Kalpakkam or Kolkata, and one can learn many things from the presentation, way of questioning, way of preparing PowerPoint, many other knowledge, a lot of other knowledge can be added to student. So my suggestion to HBNI has been that let us bring in that PhD YOOC should be offered on hybrid mode. This does not require any investment at all and no additional problem. You conduct as if you are doing the usual YOOC, except that other people are able to see it and ask questions if they want. So this is another thing which can be of great benefit to students, because you will know how others are presenting their work, what kind of questions are being asked. It could happen that the area is of interest to you, later on you will contact that person and so on. So my suggestion is that PhD YOOC can be held on hybrid from some time in the future. Professor Maiti mentioned this, I think, during this one here. For a long time, HBNI has been advocating also a study tour for the students. So this we are doing for the trainees. We can as well do it for the students. They are with us for a period of 5 years, sometimes after 6 years. In that period, why is it not possible for a student to travel to another institution under HBNI, just go and look at the facilities there and talk to some faculty, etc. for 2-3 days, and HBNI will be able to provide the travel expenditure and make all the coordination. We have already done it. We have done it for RRCAT earlier. Right now, VCC students are in Bombay. So I feel that this can be made as a regular this one. So in a 6 year, some 3-4 days is not a big deal. If it is going to give a totally new exposure to you about facilities and other places, helps you to make contacts, etc. So study tour of the students to other centers is another topic which I have, which for the students great benefit. Then the last point about HBNI's step for students is perhaps some of the students may not be aware that HBNI has taken a number of steps for the benefit of students to get exposure to industrial research during their PhD. So there is a special scheme which has been approved by the Council of Management also, by which a student during these last 2 years, after he has finished a substantial amount of work, can take a break. We call it as academic break for a period of up to 6 months. And if the student wants to spend a time in another institution, some IIT, or if you want to work in L&T, you want to work in some other organization, later on, you can this kind of contact can even help you to get placed, etc. At least it gives you an exposure to research outside your own institution. This is permitted today. This has been approved. Up to 6 months, it can be approved. Of course, doctoral committee has to examine it. And for internship in industries, already in HBNI portal, there is a provision. Students who are interested, they can register themselves, and it's possible. It's already being considered. There are students are being. Many industries are asking us, you can send your students for 3 months to 6 months. We'll take care of them. So this is already happening. So I want to just inform this also to students because many students from other institutions. So you should know that there is a possibility of internship during the PhD program in the last 2 years. So there are, so while coming back to the sharing of facilities, I want to mention one more different aspect of this. One is that having centralized facilities for very high value equipment. Second is existing facilities, how to use them across the institutions. I will give an example that I'm sure that some work being carried out in NICER for materials characterization could be very greatly benefited by carrying out SANS, small angle neutron scattering study, or something like that, which can be done at Dhruva reactor in BRC. So of course you cannot bring that facility somewhere else, but if you expand this collaboration, and I'm sure that these facilities in BARC are quite available to every one of you to carry out your experiments. It is possible to utilize very specialized equipment or reactor facilities. Same way, for example, if you want to carry out work with highly air sensitive materials, the experience at Kalpakam in handling sodium, that will be of great value. I don't know how many of you have gone and seen the liquid sodium handling facilities available in Kalpakam. So if you want to do some highly air sensitive material, you want to carry out some experiments, you can very well do it with the help of IGCAR friends. So I think that my own feeling is the takeaway from this meeting should be that the faculty or the students should not be limited by what is just available in your own group or your own CI alone. You have access, you have permission to use the facilities, knowledge base, everything across all the CIs. And for that, you need to know what is there. And that is the idea of this meeting, that there are people, there are similar working, and there are instruments and facilities available elsewhere that will give an idea. Please use it and exploit it. So that is the requirement. I personally felt after seeing all the presentations that a few years from now, if I see a presentation like this and then they say co-authors include people from NICER, BRC or IGCAR, that will be nice. And there should be co-authored papers also. Coming to that, the present national education policy as well as HBNI policy clearly envisages possibility of co-guidance. Guide from one one institution, one guide from another. I do not see why this is not implementable now, because in that case, the problem that you choose for your research is not limited by the facility available in your own place. You are having another joint guide who is obliged to provide you all the guidance, support, instrumentation, everything when required. So a student can as well go and spend the 6 months or 1 year at the another CI, carry out part of the work, come back and write the thesis, and have two guides to work with. So this is also possible. So I think we have a very large number of options, and I'm just giving a flavor of all this to you so that you can just put it in your mind and talk to your collaborators and in the future meetings, develop this further. So that was the idea of my talking here, and I am personally very thankful to Sharanappa and friends here for the excellent hospitality, and to the HBNI Central Office for inviting me to join here and share my thoughts. Thank you very much.
Thank you very much, sir, for your valuable suggestions. Now I request Dr. Himanshu S. Biswal, co-convener, give vote of thanks and conclude the session.
Good evening. We are already delayed, so I'll not take much time. But without giving vote of thanks, it will be incomplete. So, dear students, delegates on the dais and off the dais, my colleagues, and the staffs here. Hope you have enjoyed the meeting, right? All of you have enjoyed the meeting? Yeah, looking at the feedback, so have enjoyed. But for this event to be successful, there are many contributions who are not on the dais, who are sitting back there. So I'd like to thank all of them. Because of their contributions, we got so many good appreciations from them. Okay. On behalf of the organizing committee, I take this opportunity to thank all of you. We'd like to thank the students. So they are the topmost priority for us. Without them, we cannot move an inch. Thank you all of you for your efforts to make it successful. We'd like to actually, to as a brainchild from HBNI, we'd like to thank Professor Rao, Professor Maiti, Professor Naik, who is not here now, Professor Kanan, and many other members of Board of Studies who initiated this meeting. And we successfully conducted the first HBNI interaction meeting in chemical sciences. So the list is very long. We are thankful to our director, Professor Ponda, who also encouraged us to conduct this meeting. We are really grateful to him. The students' participation from all the students, from the integrated MSc students, integrated MSc PhD students, postdoctoral fellows, research associates, the GRF and SRF were there, project assistants. So all of us contributed enormously to make it successful. So thank you all of you. In fact, the involvement and tireless help from the students, volunteers, we are sitting there and some of them are maybe in the outside looking for the food arrangements. So we are really grateful to those students. So some of them could not sleep also to attend, to go to the airport, to attend the transport services, food services, all that stuff. We are really grateful to the student volunteers. So many of our faculty colleagues, I cannot name all of them. So they also worked a lot. So starting from making the stage to work properly, making the audio video visuals to work properly. The food arrangements have been done nicely. It was led by Dr. Purohit. The transport service was the car, the bus, all the services was led by Dr. Sharma. He is sitting here. The abstract and many other services. The abstract and making the program schedule was by Dr. Vishnu Vishwal and Dr. Bhargav here, PL Bhargav. And not only those, many other colleagues also, they contributed a lot actually to make this happen. So thank you all of you for those, for your efforts. So the assistance provided by the auditorium in charge, the purchase and finance section, the computer center, central library, IWD section, the photographer who is sitting there. So their contributions also we can never forget. So these are little contributions, but it make it decorative and make it successful. We also thank to the caterer service. There were little problem in the past day. So we take this responsibility and we apologize for that. And we hope they improved in second and third day and you enjoyed the food served by the caterer. And thank you. We would like to thank them for their service. We are thankful to our sponsors. So they are very generous. Almost eight sponsors. They financially supported and because of what we have like memento, all other stuff, the stages. So we'd like to thank the sponsors, the INCARP Instruments, Laser Science, Thermo Fisher Scientific Instruments, MN's Survey, the Class 1 and S&P, Piper Vacuum, IR Technology Services, Blue Ocean E-Commerce Limited. So none of them are here, unfortunately, but they have supported us to make it successful. The list, as I said, the list is long. If I have missed any of them, please excuse me. We appreciated all your time contributions. It is a big for us. Okay, so the last but not least, actually, I would request Professor Srinivasan. We have three colleagues, three staffs in our department. We thank all the teaching, non-teaching staff of our department for their generous support. But there are three staffs of our department who worked actually sleeplessly, and we'd like to felicitate in this validated function. Professor Srinivasan. Yes. So may I call Mr. Sanjay Patra? We have a very small gift for them. Yes. Mr. Sanjay Patra. Okay, he takes care of our department, mostly almost all administrative services. So the next one is Mr. Chittaranjan Naik. Can you give a big hand of applause to him, Chittaranjan? Okay, so the last one is favorite for all. Okay, so his name is Subrat. Subrat, could you come here? He's very favorite. You will not find him walking, always he runs. Subrat, there could you call him. He might be running to arrange the fees and snacks, looks like. Okay, we'll take him. So thank you again. Thank you all. If I have, as I said, if I have missed any name, so please excuse us. So I thank all of you again and again for this meeting to happen, and it was successful also. So with this remark, this thanksgiving, we can conclude the session with our family's permission. Okay. Thank you. Hope we'll meet again in the second HBNI interaction meeting in Temple Center, somewhere in BRC or IGCAR or that. Thank you.
Thank you all. High tea is arranged at the outside of the auditorium. Please join. And also I request all poster prize winners come to the dais. All poster prize winners, please come to the dais. And also please note that outstation delegates, today's dinner and tomorrow's morning breakfast is arranged at the same cafeteria place. Please, yeah.
Poster prize award winners, please come to the dais for one final. I request all poster prize winners, please come to the dais. Along with your certificate, I need your signature. Please hand over. Will little bit correction will do, and again we'll give it back to you, please. Please. And also one along with this one, we'll take one group photo. Please.